Hello everyone, very good afternoon and welcome to the BYJU'S exam prep, the most comprehensive app for all competitive exams. How are you guys? And this is a very important session for EDC, that is electronic devices and circuit, and it is a revision marathon for GATE 2024. I think sound quality, picture quality, everything is fine. Please check and inform me. Everyone. Yes, please. Okay then. Uh, okay. Is it audible, guys? Very good afternoon, everyone. Chinmay and all other students. Now, here in this session, we will discuss what important topics from EDC. It is a quick revision of EDC, and then we will discuss what semiconductor physics, PN junction, and then what BJT, MOSFET, MOS capacitor, and what special diodes. I think all are ready. Okay then. Now, here it is a revision marathon. First of all, subscribe our channel, guys, and this is my Telegram channel. You can join. I will upload the PDF of this session on this electronics by Sanjay Rathi for daily dose to improve concept. If you have any doubts, then you can post, and to get the notification of any particular exam, you can join this, and I will upload the PDF of this session on electronics by Sanjay Rathi. And then this is my introduction, 23 years of teaching experience, and these are my ranks in engineering services exam, right? And I have trained more than 1 lakh students for these competitive exams. Then first of all, share the link of this session so that the student will join, guys. Okay, everyone, please share the link. Now, okay then. Sir, special diodes, please take the Okay, I will take my special diodes. I'm going to cover here. So that is on. This is the schedule, revision marathon, upcoming schedule, guys. You can note, and that change the date. That is on what 16th of January. I'm taking the EDC, then EMFT, 17th or 18th Jan, then 20th of Jan engineering mathematics, then 21st January engineering mathematics part 1, part 2, and then 23rd January signal and system, guys. Daily at 10 a.m. Please note the time, guys. Okay. Then you can scan this QR code. Everyone, please first of all scan this QR code, and after that session you can join the mock test on our app, that is BYJU'S exam prep app. Okay, BYJU'S exam prep app. You can join for mock test. So first of all install that from Google Play Store, and then go for what mock test, and scan this QR code. Okay then, first of all, just I'm going to start this important parameters. Get the idea about important parameters. Sometimes they will provide you the important parameters, or sometimes we have to use these parameters. So what are these parameters? Electronic charge, rest permeability, permittivity of free space, Planck's constant, thermal voltage, that is called VT, KT by Q, right? That is the value 0.259, as you know. Then important standard constant for silicon, how many number of atoms. For germanium, how many number of gallium arsenide, then what is the germanium. Dielectric constant. Okay, तो ये dielectric constant हो गए. Then this is important for silicon, that is 11.7. sometimes it is given as a 12, and that is for germanium. And the band gap, sometimes we are getting direct straightforward question on band gap or Fermi level. When we want to solve question on Fermi level, get the idea about the band gap. It is 1.12 electron volt for silicon at room temperature, or that is what 0.72 or 0.74 electron volt for what germanium. So we that is the value, and these are called effective density of states in conduction band. That is, this is the value of NC. Then that is the value of NV. Last time we got one question on what NC and NV, standard density of state in conduction band and in valence band. So the effective density of state in conduction band, effective density of state in valence band, that is the value of the NV, but especially for silicon, this is important. For silicon, it is important. And then intrinsic carrier concentration, again that is for silicon, it is important, then that is for germanium. And mobility, they will provide you the data for mobility, but sometimes if you want to compare, what is this electron mobility is 1350, nearly equal to, and that for germanium 3900. And what is the mobility of hole? 480 for silicon. So 1350 divided by 480, it will be between 2 to 3. That is the ratio of mu n by mu p is 2 to 3, and mu n is always greater than mu p. Similarly, 3900 upon 1900, you will get the between what ratio will be between 2 and 3, mu p by mu n or mu n by mu p. Mu n is greater than mu p, right? Mu n is greater than mu p. Then, now why semiconductor? Why we are preferring the semiconductor? Controlled conductivity, first of all. Second, low power consumption. And third is smaller size. That's because of this we are preferring semiconductor like silicon, germanium. These are the indirect band gap semiconductor, and third is direct band gap is gallium arsenide. Example of direct band gap, if you want to design LED, light emitting diode, then direct band gap semiconductor is required, guys. So that is the case. Now, next one is classification of solid state material. So basically semiconductor, when we are classified on the basis of energy band diagram or what that is the material, so we are using insulator, conductor and what semiconductor. The conductivity of semiconductor is between what insulator and that of conductor. Conductivity is very high. Insulator, ideally the conductivity is 0, but it is very low. And for semiconductor, this is the range of the conductivity. But no one is going to ask you the range, so don't try to mug up. Don't try to mug up. Okay, that is important. Then guys, I will give you the idea, Vikram, at the end. When that is the gallium arsenide of phosphorus, we are changing the percentage of phosphorus, then what will happen? At the end you will get the idea. Then energy band diagram means what? When this gap conduction between the conduction band and valence band, this is called conduction band, this is called valence band, and this is the one level, this is called EC. EC is the lowest energy level of the conduction band, EV is the highest energy level of the valence band. EC minus EV is called forbidden energy gap. Forbidden energy gap. If this gap is greater than 5 electron volt is the unit of energy. What is the 1 electron volt is equivalent to? Everyone give me the value. This is equivalent to how much joule? 1 electron volt. So this gap is, if it is more than 5 electron volt, then it is an insulator. For semiconductor, the gap is nearly equal to 1 electron volt. Nearly equal to 1 electron volt. And for conductor, there is no gap. There is no overlapping of valence band and what? Conduction band. Okay, so the overlapping of valence band and conduction band, guys. Now, next one is, I think, what is the, so tell me what is the 1 electron volt means? 1 electron volt is equivalent to how much joule? So, and on the energy band diagram, we can classify it into 3 categories. That is called what? Conductor, insulator and what? Semiconductor. 1.6 into 10 raised to power minus 19. Muhammad Anwar, yes, you have given the right answer. If you want to convert the 1 electron volt, then simply this is in joule, means it is a very smaller unit of energy. It is a very smaller unit of energy, guys. And if you want to, in 1 joule, how many electron volt means? From this you can find 19 electron volt. So that is, in this way you can convert the electron volt into what? Joule. बिल्कुल सही है. Now basic चीजें हैं. Then give me 1 minute. Now, atomic structure, that is the periodic table. For get the idea about that. That is Bhanu Prakash. Very good afternoon. Thank you, Mohammed. Now, periodic table means third group, fourth group, and fifth group. So, in a fourth group, we have carbon, silicon, germanium, strontium, and Pb, and what 5. But these two are important, silicon and germanium. Then fifth group, we have to add this so that we can get the extrinsic semiconductor. So phosphorus, arsenic, we are normally adding phosphorus and arsenic, but remember bismuth also, it is of fifth group. This is the fifth group material, and this is the boron, aluminium, gallium, indium. These are the third group element, guys. Third group element. So please remember all these points, right? ऐसा मतलब ये आपका 3 है. Now, तो ये third group, fourth group and fifth group. So normally we are using the fourth group, that is the silicon and germanium, as a pure intrinsic semiconductor. Or when we are adding the fifth group element, then we are getting what? N-type semiconductor. When we are adding the third group element, then these are the acceptor. It will accept one electron and create the hole. Then that semiconductor will become P-type. When we are adding the third group, then it is of P-type. So this is the semiconductor. Now, atomic structures is like this. For silicon atom, what is the atomic number of silicon? What is the atomic number of silicon? Right, 14. Atomic number of silicon is 14. Okay, this is 284. Or atomic number of germanium is what? 32. So that is the 2, 8, 18 and 4. So at outermost orbit, so that is the arrangement. So this is the germanium. So in germanium, the distance between the outermost and this nucleus is what? High as compared to what? Silicon. Distance between the outermost, these are called valence band, valence orbit. This is the valence orbit. Here we are having the 4 electrons. Again here we are having the 4 electrons. So that is the silicon and that is the germanium. Then, and that is the atomic number 32 for germanium and 14 for what? Silicon atom. These are the, we are having the covalent bonds here, right? There is a covalent bonds in case of germanium and silicon. Covalent bonding means sharing of electrons. In intrinsic semiconductor, we are getting this type of structure. That is the sharing of the electron between neighboring atoms. This is the sharing of the electrons between the neighboring atoms, right? So this is the covalent electrons. Now, so you have idea about this, so because that is the we are getting MSQ type of questions. So that's why. Now, already I have given EC and EV. There are 2 bands. One is called valence band and one is called conduction band. Okay, tell me guys. In case of germanium, what is the energy band gap at 0 degree Kelvin? At 0 degree Kelvin, what is the EG for germanium and what is the EZ for silicon? Tell me. This is the band gap. This is called conduction band and that is called valence band. It is a filled state at 0 degree Kelvin. All the electron will be in what? Valence band. And there is no excitation, and that's why at 0 degree Kelvin it behaves like what? Insulator. It behaves like insulator because all the electrons will be in valence band no electron in conduction band, therefore the conductivity of that semiconductor material is 0. One student have Muhammad Anwar, you have given the 0.3, Surendra, you have given the 0.7. This is the actually 0.785 electron volt, exactly at 0 degree Kelvin, 0.785 electron volt, guys. Remember this. Okay. So this is the case, and when temperature increases, it will decrease beta T. Now exactly at T equal to 300 degree Kelvin, Eg will become 0.72. So you can find the value of the beta also. Right, this is the band gap, energy gap. So you can put the 300 degree Kelvin, this is the value at 0 degree Kelvin minus beta T. You can find the value of the beta T because it is the at 300 degree Kelvin, the value is 0.72. Similarly for silicon it is 1.21. For silicon it is 1.21, and exactly at room temperature 300 degree Kelvin it is nearly equal to 1.1. 1.1 means temperature increases, band gap decreases. And at 0 degree Kelvin, all the electrons will lie in the valence band. There is no holes and no electrons, no free electrons in conduction band. Remember, that was the question last year. Then, okay, when we are increasing the temperature, what will happen? The electron will get the sufficient energy and switch from valence band to conduction band. A new hole electron pair generated. Electron is moving from valence band to conduction band, and it will create what? Holes in the valence band. Hole means simple vacancy. This is the vacancy in valence band, guys. So hole will lie in the valence band, electron will lie in the conduction band. So that is the case. Now when electron hole pair generated, conductivity will increase. So I will give you the formula of the conductivity, sigma. Right now, when under controlled condition, when electron falls from conduction band to valence band, it is called generation. Electron is moving from valence band to conduction band, new whole electron pair generated. Concentration of electron, when I am talking N, means this is the concentration of electron in conduction band. When I am talking the P, concentration of hole, that is in what? Valence band. Temperature increases, new whole electron pair, N increases, P increases. Or in case of intrinsic semiconductor, N is equal to P is equal to Ni, always remains same, intrinsic carrier concentration. So already I have given for silicon, it is 1.5 into 10 raised to power 10 per centimeter cube. That is the unit per unit volume. This is called concentration. Okay, 1.5 into 10 raised to power 10 per centimeter cube, guys. Now, this is the very up when under control condition, when electron fall from valence band to conduction band, then there is a recombination. So here energy is required for excitation. Energy is required to switch the electron from valence band to conduction band, and when the electrons switch from conduction band to valence band, it will give the energy. It will give the energy. If it is an indirect band gap semiconductor, for example germanium or silicon, it will give the energy in the form of heat, and that's why temperature of lattice structure increases. But if it is a direct band gap semiconductor, like what gallium arsenide, then what will happen? It will give the energy in the form of what? Light, and that is the concept of LED, light emitting diode. Concept of LED, light emitting diodes, guys. So this is the process of merging an electron from the conduction band with a hole in the valence band is called recombination. When the electron falls from conduction band into the valence band into the hole, a recombination process occurs and electron hole pair disappear. Electron hole pair disappear. Acha, tell me how we can increase the recombination rate. मतलब जैसे recombination slow हो रहा है, तो how we can increase the rate of recombination? Do you heard about anything? क्या mix करते हैं भाई? We are introducing something so that the rate of recombination will increase. Okay, so that is the case. This is called recombination. In the indirect band gap in the form of heat energy, or direct band gap in the form of light. So during recombination it will deliver the energy and electron hole pair will disappear. That is the recombination process, right? Hole, what is the hole? Hole is the what? Vacancy. Always remember, when bond will break, when the bond will break, what will happen? Electron will switch from valence band to conduction band, and there is a vacancy is created, or it is what? Positive by doping impurity. No. Mohammed, I am saying that we can increase the recombination rate by introducing what? Gold, right? Gold. That is called recombination center, trap, recombination center. So when we are introducing the gold, recombination rate will increase, right? And that is the case. So hole, actually hole is what? Positive charge carrier. So positive charge carrier means, suppose this is the holes. When under the influence of electric field, if suppose the holes are moving in this direction, then the charge is moving in this direction, and what will be the current rate of change of charge? That is positive. If the hole is moving in this direction, current is also moving in the same direction. Same direction. I will give you the formula of drift current and diffusion current, because that is important. Drift and diffusion, what is drift, what is diffusion, what is the Einstein equation. So quick revision. Now please stay tuned with me, because it is a very long session, guys. It is started from 1 p.m. It will continue up to what? 7 p.m. around approximately around 5 to 6 hours. Within 5 to 6 hours, complete revision of what? EDC. I will give you the break after 2 hours. I will give you the break, 10 to 15 minutes. But please use your note copy, right? Pen, calculator, okay, and note the topics. If you have any doubt, then you can ask. And after the session, at the end, I will give the password, protected PDF. I will mention the password, and I will upload the PDF on my Telegram channel, that is Electronics by Sanjay Rathi. So it is a quick revision, and that is the day for what? EDC, guys. Okay. Then hole. This is about the hole. Hole is a positive charge carrier. Now, when we are talking about the current density, guys, current density, what is the current density equation? As you know, very simple. J is equal to what? Sigma E. E means applied electric field. For example, if you have any bar, because normally we are getting this type of questions. We are applying the voltage here. Length of the bar L. This is the V. Then what is the electric field? V by L. Normally we are using the unit volt per centimeter. Volt per centimeter. Remember that unit. Then J is equal to what? Sigma E. Sigma is called conductivity. Conductivity is given by NQ mu1 if it is of electron into E. Or J will become PQ mu P into E. That is the conductivity because of the electron, because of the holes. Mu1 is the mobility of electron, mu P is the mobility of holes. Okay. Then this is called current density due to the electron. Some students are confused. I by A. Remember the current density I by A, or we are calculating the I ampere, or area is normally in centimeter square. Ampere per centimeter square, that is the unit of current. Right? Yes, now you can start. If you are going to give, then how many subject you have prepared? Tell me. Then that is the electric field. This is one important topic. From this point we can get 1 mark question or 2 mark question in EDC, guys. Don't take it lightly. And then how find the electric field, find the current, and what is the current density, and so on. But it is a simply drift current density. It is a drift current density under the influence of the electric field, and concentration is uniform. There is no concentration variation, and that's why there is no chance of what? Diffusion. No chance of diffusion. And we are talking about the drift current density, guys. Okay. Now, so this is the current because of electron and because of what? Holes, guys. Now what will happen? In intrinsic semiconductor, N is equal to P is equal to what? Ni, that is called intrinsic carrier concentration. That's why sigma E, this is given by NQ mu N plus PQ mu P into E. That is the conductivity because of electron and holes, but N and P are equal. That's why it will become NIQ mu N plus mu P into what? E. Now, in case of intrinsic semiconductor, the concentration of electron and concentration of hole are equal. Then what will be the contribution of hole and electron in conductivity? Tell me, guys. Because of hole and because of electron, what is the contribution? The contribution of electron is equal to contribution of holes. Contribution of electron is greater than that of holes. Contribution of electron is less than that of hole in conductivity in case of intrinsic semiconductor. Which option is correct? A, B, C. A, B, C. We have the same concentration of what? Electron and holes in case of intrinsic semiconductor, and we have the conductivity both because of electron as well as holes. Then contribution of which one? Both have the equal contribution or different contribution? Right. Now you are giving the option A, guys, equal contribution. But remember, there is a no doubt. This is the concentration are same. N is equal to P is equal to Ni. But what about the mobility? Mobility of electron is greater than what? Mobility of holes. So mu N by mu P is almost 2 to 3 times. So guys, it also depends upon the concentration. It also depends upon the mobility. So mobility of electron is high, and that's why the contribution of electron is high as compared to that of holes because of mobility in case of intrinsic semiconductor. Are you getting my point, everyone? This point is clear to you? Okay then. So electron has more effect on conductivity in case of intrinsic semiconductor because of mobility. Okay then. Next. So now guys, what will happen? Again, in case of intrinsic semiconductor, we are getting the conductivity because of electron as well as because of holes, but the conductivity is very low. Very low. As then what will happen? We are giving the doping. Doping means we are adding the impurity to increase the concentration of either holes or electrons so that we can increase the conductivity because conductivity depends upon the concentration. Then the doping. So intrinsic semiconductor, that is the shape of the intrinsic semiconductor, covalent bonding and so on, sharing of the electrons. Now what and why doping? In the semiconductor terminology, the addition of the controlled amount of specific impurity atoms. What are the specific impurity atoms? Pentavalent or what? Trivalent. Already I have given you the trivalent or pentavalent, or you can remember this way: big. I'm not talking about any party. Then this is the boron, indium, gallium, and that is the arsenic, right? Or what? Phosphorus and so on. Then antimony, arsenic, phosphorus. Now in a semiconductor terminology, the addition of controlled amount of specific impurity atoms with the purpose of increasing either the electron or hole concentration is called doping. Now this is the trivalent. It will accept one electron and become the negative ions, and that type of ion is called acceptor ion. Acceptor ions, and it will increase the concentration of hole, and these will increase the concentration. It will donate one electron and become positive ions. Concentration of electron increases, and that's why this type of semiconductor is called N-type semiconductor. N-type of semiconductor. क्या मोहम्मद क्या पूछ रहे हो? Please explain. It is not equal ना, not equal. Mobility of electron is greater than mobility of holes. No doubt the concentration is same, charge is same, but what about the mobility? Mu n is greater than mu p, and that's why NQ mu n is greater than what? PQ mu p. Why? This is same, this is same, but mu1 is greater than mu p, and that's why the contribution of electron is more as compared to contribution of hole. Now it is clear. Watch this now. N q mu n is greater than p q mu p. No doubt n and p are equal, q and q are equal, but mu n is greater than mu p. Mu n is greater than mu p. Okay, so there are two types of extrinsic semiconductor. One is called n type, one is called p type. Now, extrinsic semiconductor, in already I have given, this is the when we are adding the trivalent or we are adding the pentavalent. Trivalent means these are the material, pentavalent these are the material. You can take a screenshot, or otherwise I will upload the PDF on my Telegram channel, guys. So normally we are adding what? Boron, indium, gallium, okay. Or here we are adding what? Phosphorus, arsenic, bismuth, antimony, and so on. This is the antimony means Sb. Remember, this is the antimony, Sb. Okay, then now n-type semiconductor means what? When we are adding phosphorus, for example, so it has in outermost orbit, it has what? 5 electrons, and out of which 4 will be involved in the bond, and it has 1 extra electron. It will donate 1 extra electron, and that's why we are increasing the concentration of electron when we are adding what? Pentavalent impurity, guys. Now what about the structure? Watch this. In n-type semiconductor, you will get this type of structure in energy band. This is the conduction band, this is the valence band, or here we are having one discrete donor energy level near to what? Conduction band. Exactly at 0 degree Kelvin, always remember there will be the question, exactly at 0 degree Kelvin what will be the nature? It is insulator. Whether it is intrinsic type semiconductor or extrinsic, it is insulator at 0 degree Kelvin. But when we are increasing the temperature, two things will happen. We are having the discrete donor energy level, that electron will switch from this level toward conduction band, and the concentration of electron increases in conduction band. At the same time, some electron will switch from valence band to conduction band. So when the electron switch from donor energy level to conduction band, that is called extrinsic excitation. Extrinsic excitation. Extrinsic excitation. And when the electron switch from valence band to conduction band, that is called intrinsic excitation. Intrinsic excitation. So how many types of excitation here? Two types of excitation. One is called intrinsic, one is called extrinsic. Now what I want to say, that is important. Exactly 0 degree Kelvin, it is insulator. But when we are increasing the temperature, then initially the conductivity will increase because of what? Extrinsic excitation. More electron will switch from donor energy level to what? Conduction band, and that's why the conductivity increases because of extrinsic excitation. But at room temperature at 300 degree Kelvin, almost 100% extrinsic excitation done. Almost 100% extrinsic excitation done. Then what will happen? Again, when we are increasing the temperature, now intrinsic excitation will start. Intrinsic excitation means now the electron will switch from valence band to what? Conduction band. Valence band to conduction band. So after 300 degree Kelvin, if we are increasing the temperature above 300 degree Kelvin, again the conductivity will increase, but this is because of what? Intrinsic excitation, right? Yes, Vikram. Extrinsic excitation will not generate what? Electron hole pair, because it will generate what? It has 1 extra electron, it will donate it, and it will generate what? Ion. This is called donor ions. Donor ions. So a very simple thing. Two things will happen. When there is a intrinsic excitation, 1 electron will generated, 1 hole is generated. Both are neutral, positive, negative, neutral. But in case of extrinsic excitation, it will donate 1 electron and become positive ion. This is positive ion, this is the negative, positive, negative, neutral. If we are giving the trivalent impurity. It will accept one electron, it will become what? Negative, and it will generate holes. So these are the pairs. These positive is not a, what is the positive? It is a immobile charge carriers. It is a immobile charge carriers, guys. Okay. So this is the immobile. I will solve some selected numericals also. So these are called, suppose we are having this positive donor ions as well as electron. So this is called covered. Covered means it is neutral. Covered means it is a neutral. Positive, negative, neutral. Similarly, this is covered, neutral. Negative, positive, holes and acceptor ions. But once hole is moving or electron is moving away from this, these are called uncovered. Uncovered immobile charge carriers. Immobile. Immobile means under the influence of electric field, they will not move. They will not move, guys. So that's why they are not going to contribute in what? Current. Remember, they are not going to contribute in what? Current, because it is immobile charge carriers. But it will generate what? High electric field region. High electric field region means, if suppose any, here we are having the negative ions, here we are having positive ions, here we are having the negative ions. This is the plus charge, this is the minus charge, and there will be the electric field from positive to negative. And that is the concept of what? Diode. So in diode, I will give you the more detail about this, how we are going to generate the electric field, guys. Okay. So up to this point, any doubt? Just I have discussed the very, very basic thing about the semiconductor physics. Semiconductor physics. Okay then. Then what are the majority and minority carrier? In case of N type, majority carriers are electron and minority carriers are holes. Why? Because the concentration of electron is very, very greater than concentration of holes. So majority carriers are electron and minority carriers are holes, guys. Then P-type semiconductor, we are giving the boron, trivalent impurity. Then this is the boron. Then we have one discrete energy level, that is called acceptor energy level. What will happen? Exactly at 0 degree Kelvin, again it is an insulator. At 300 degree Kelvin, it will accept one electron here. This is called extrinsic excitation, become negative ions, and here hole created. But what is the concentration of electron in conduction band? Almost 0. But at the same time, some electron will switch from valence band to what? Conduction band. This is called intrinsic excitation. So we have few electron in conduction band, but very, very less. And this is concentration of electron is less, or concentration of hole is very, very high as compared to electron, and conductivity is mainly due to holes. That's why it is called P type. That's why it is called P type. Very, very simple. And EA, they will ask, what is this? Discrete acceptor energy level. The gap between this is very, very small, and gap between EC and EV is 1.1 electron volt for germanium. And this gap is nearly equal to 0.1 electron volt, right? So remember that 0.1 electron volt, this gap. Then P-type semiconductor means what? Concentration of hole is greater than concentration of electron. Now what is the meaning of the compensated semiconductor? Compensated semiconductor. So we have N-type semiconductor. N-type means we are giving the ND doping donor. It will donate one electron. Here the concentration of N is very, very greater than P. P-type. Here we are giving the acceptor impurity. It will accept one electron and it will increase the concentration of hole. Now there is a compensated semiconductor, is one that contains both donor and acceptor impurity atoms in the same region. Compensated means we are giving Na as well as what? Nd. And so on. This is called compensated semiconductor, guys. So here no, it is not case that both have the same. So what will happen if we are giving the Na as well as Nd, and there are different cases, guys. N types compensated semiconductor occurs when Nd is greater than Na. When the Nd is greater than Na, then what will happen? This is called what? N type. Then P type compensated semiconductor means Na is greater than Nd. And then if Nd or Na both are equal, we have a completely compensated semiconductor that has the characteristics of an intrinsic material almost. This is called completely compensated semiconductor material, where Na is equal to what? Nd. Na is equal to Nd. Right? So we are just already I have given that this is the. So that is the case. Sometimes they are giving you the numerical. In case of compensated means what? You have to use the two law. One is what? Law of neutrality, and one is called mass of, right? So we will use this mass action law and what? Law of neutrality to solve this type of questions. Then, so what are the current density, guys? So this is the, I think now it is clear, compensated semiconductor when both Nd is given as well as Na is given. And now we will solve some numerical. I will give you the formula how to find the concentration of electron and how to find the concentration of hole in case of compensated semiconductor. Then this is the current density. So already I have given in case of intrinsic semiconductor formula, and that is in case of what? Conductivity sigma. Ni is the intrinsic carrier concentration. That is the conductivity. This is the N type semiconductor. N type semiconductor is what? Concentration of N in N region, mu N. Concentration of hole in N region, mu P and E. That is the formula for the conductivity. Current density, J. And that is the property of N type of semiconductor. That is the conductivity actually. Very, very simple formula. Remember, concentration of electron is very less in P type of semiconductor. Speed. Okay. What is the mass action law? So quickly, this is a quick revision, guys. If you find any difficulty, then please, the donor high, it is N type. Now, Muhammad, we can say, but we at the same time we have to find the concentration. So I will give you the formula. From that you can find the formula. Directly we can't say, na. Directly we can't say. I am going to give you one formula also. Then, what is the mass action law? Law of mass action states that the product of majority carrier and minority carrier is constant at fixed temperature and is independent of an amount of donor and acceptor impurity added. Mathematically, it is represented as Np is equal to Ni square. Np is equal to Ni square, guys. It will remain constant. Okay? Np is equal to Ni square. And this is the law of neutrality, because the charge of the electron is negative. Charge of the acceptor ions is also negative. This is electron. And charge of the hole is positive and charge of the donor ion is positive. That's why negative charge is equal to what? Positive charge, and that's what is called law of neutrality. They will cancel each other and there is no charge. So Nutan Kumari, how are you? Very good afternoon. चलिए आपका लंच टाइम भी हो रहा है, सबको बुला लीजिए भाई, प्लीज कॉल. चलिए ज्वाइन कीजिएगा. इट इज अ क्विक रिवीजन. अप टू 7 PM यू विल गेट द आइडिया अबाउट EDC, इलेक्ट्रॉनिक डिवाइसेस एंड सर्किट. So that is the law of neutrality. Now, when I am talking about the mass action law and law of neutrality, for example, it is a compensated semiconductor. When Nd is greater than Na, so what is the concentration of electron that is given by Nd minus Na by 2 plus root over nd minus na by the 2 plus 2ni square, guys. So that is the formula. This is the formula. Yes, if there is any doubt, or you can verify this formula by what? This formula, this one. Always remember this formula. This is the first equation, mass action law. If you want to find the concentration of electron, then you can find the Ni square by n. This is the concentration of hole, and then because Nd is greater than Na, what is the law of neutrality? N plus Na, P plus Nd. Now, if you want to find the concentration of electron, then you can replace the P by Ni square by n. Since Nd is greater than Na, you can put here, it will become Ni square by n, Nd minus Na minus n. But are you getting my point? This is a very simple thing, and our right hand side, that will become Ni square by n plus Nd minus Na, and now you can multiply it. Minus what? N square. Actually, you want n, so you can write the quadratic equation like this: n square minus Nd minus Na minus Ni square. Okay, that is a very simple, and now you can find the concentration. Quadratic equation: minus B plus, there is a plus minus root over B square minus 4AC. It will become minus minus plus, minus 4AC upon 2A. What is the A? 1. Okay, and now you can divide it, so it will become, why we are ignoring the minus sign? Any idea? Plus Ni square, because this 2 will become 4, 4 cancel. This is the formula. Why we are ignoring the minus sign? Now remember, in this case, just ignore this minus sign, because concentration, that concentration is always positive, guys. Concentration of electron is always positive. So Nd minus Na by 2 plus root over Nd minus Na by 2 the whole square plus Ni square, that is the formula. Okay, that is the formula for this. Now sometimes what will happen, this Nd minus Na by 2 the whole square is very greater than Na. Now if this gap, you can ignore, and then it will become, concentration of N will become Nd minus Na. Nd minus Na only, that is the concentration of electron. But that will be the case when Nd minus Na by 2, this is very greater than Ni. Then you can ignore the Ni, and then it will become this formula, Nd minus Na. Nd minus Na. Okay, and from mass action law, you can find the concentration of holes. So sometimes we are getting this numerical. Objective, this is the objective numerical we are getting. Okay, so if you find any difficulty, then always use these two formula, mass action law and law of neutrality. Then, is it clear? Any doubt? This is clear to you? This 2 when enter into the root, it will become 4. So Nd minus Na by 2 the whole square, and this 4 and this 4 is cancelled out. That's why we are getting Ni square here. Okay. Arey, Muhammad, how you are derived? I have derived what? This is the mass action law. That is the law of neutrality. Simply replace the P by Ni square by N, or get the quadratic equation. This is the quadratic equation. Solve the quadratic equation. What are the roots of the quadratic equation? Roots is what? Minus b. So minus b means what? Minus minus it will become plus. Plus minus root over b square nd minus na the whole square plus 4ac to minus. This will become what? Plus na or minus. Is it correct? B square minus 4ac to minus minus it will become plus. Upon that is the value. Very simple. Okay then. The next one. Similarly in p type you can find, but in a p type what will be the change? If it is a p type semiconductor, then what will be the change? The change is simple. Na minus Nd by 2, Na minus Nd by 2, everything will remain same. Na minus Nd by 2, that is the concentration of what? Holes. And then from mass action law you can find the concentration of electron. In place of p, replace the n. P is replaced by n is replaced by p. Very simple. You can find. Now then there is a very very important point is what from where we are getting the question, Fermi direct functions. Fermi direct function, guys. Okay, so this is the distribution function. It is a probability distribution function, right? And from this we are getting the probability of finding an electron at particular energy level. What is the probability of finding an electron in? So this is the case, the probability that the available energy state will be occupied by an electron at absolute temperature under condition of thermal equilibrium is given by the Fermi direct function. It is only gives the probability of occupancy of the state at a given energy level, but does not provide any information about the number of states available at that energy level. How many number of states are available? We are not getting any idea. Just whether it is occupied by electron, yes or no, and what is the probability there. So that is the case, and this is the formula. 1 upon 1 plus E minus EF by kT, where E is the energy level, EF is the Fermi energy level, K is the Boltzmann constant, and T is the temperature. And E is the energy, any energy level, or exactly at E is equal to EF. This will become 1 by 2. So Fe is 1 by 2, 0.5. That will be the question. What is the probability of finding an electron exactly at this Fermi energy level? That is the 0.5, irrespective of what temperature. At any temperature, because E minus EF will become 0, it is independent of the temperature. So at all temperature, at exactly at Fermi energy level, the probability is 0.5. Probability is 0.5. This is a last year there was a question on this formula, guys. Please revise this formula 2 to 3 times. And now when we are plotting the curve, we are getting this type of curve, guys. This type of curve means this is the curve exactly at 0 degree Kelvin. What will happen at a 0 degree Kelvin? All the holes will, all the electrons will be in valence band. And what about the concentration of electron in conduction band? 0. So concentration of electron in conduction band is 0 when the E is greater than EF, or the concentration of holes in the valence band is 0 and concentration of electron in valence band is 100%, exactly at 0 degree Kelvin. This is the conduction band and that is the conduction band, right? And that is the Fermi level. If there is an energy level below this, means this is the, so what is the probability of finding an electron? 100%. Exactly at 0 degree Kelvin, all the electrons will be in valence band. And what is the probability of finding an electron in conduction band? 0. So when the energy level is greater than EF, so this is the area where E is greater than EF. This is the area where E is less than EF. So what is the probability here? 1. What is the probability here? 0. Exactly at 0 degree Kelvin. But when we are increasing the temperature, few electron will switch from valence band to conduction band. Then probability of finding an electron in valence band will reduce and the probability of finding electron in conduction band will what? Increase. So there is a reduction. Watch this. Reduce. Probability of finding an electron in valence band reduces. In conduction band it increases. Conduction band it will increase, guys. So we are getting question. So that type of shape means this is the for temperature more than what 0 degree Kelvin. For example, 300 degree Kelvin. That is the curve. So probability of finding an electron decreases, probability of finding electron in conduction band increases. This is the E less than EF, that is the E greater than EF. Okay, probability. Then this is the important formula. NC means this is a subscript NC. EC minus EF by KT, minus of EC minus EF by KT, and this is the concentration of electron, and that is the concentration of volt, NV e raised to power minus EF minus EV by KT. These are the two important formula. From this you can solve question based on what Fermi level. These are the two important formula. कई बार क्या होता है, मगअप कर लेते हो, पता नहीं होता है कैसे आ रहा है, राइट? मगअप किया आपने, this is applicable for only compensated, sir. Compensated, or if suppose NV or ND is 0, then yes, you can take it what 0. Then again you can solve. Okay then. So this is the formula. EC minus EF means EF is the Fermi energy level, EC minus EF is the gap between the Fermi energy level and conduction lowest energy level of the conduction band. Then this is the EF minus EV by KT. This is the concentration of hole in valence band, that is the concentration of electron in conduction band. I am talking about the conduction band. EC minus EF by KT. Or NC is called standard density of state in conduction band, standard density of state in valence band. So which one is higher, NC or NV? Tell me. Which one is higher, NC or NV? Now, in case of intrinsic semiconductor, we are getting the Fermi energy level in between, but normally we are saying EF is equal to what? EC plus EV by 2. Is it correct? Is it correct? EC plus EV by 2 in between the valence band and conduction band. But in this case, actually what we are assuming, NC and ND are equal. NC and NV are equal. And that's why it is exactly in the middle of what forbidden energy gap. But that is not the case. That is not the case, guys. Here we are getting the Fermi energy level, where in case of intrinsic semiconductor we are getting, this is, if suppose this is the middle level, exactly middle level, this is the middle level, this is the EC plus EV by 2. What about the Fermi level? Just above what? Middle level, just above the middle level. Okay, so that is the case. And which one is higher, NV or NV is greater than NC? Because it depends upon what? Effective mass of holes. NV depends upon the effective mass of holes and NC depends upon the effective mass of electron. And effective mass of hole is greater than what? Effective mass of electron. Effective mass of hole is greater than effective mass of electron. And therefore, mobility of hole is less than mobility of electron. More will be the effective mass, less will be the mobility. So effective mass of hole is greater than effective mass of electron, and NV depends on what? Effective mass. NC also depends upon the effective mass of electron. NV is greater than NC. NV is greater than NC. Remember, if under ideal condition, what we are assuming, effective mass of hole and effective mass of electron are equal, we can say NV is equal to NC. Under this condition, this is the formula. Otherwise, what is the exact formula? I am going to give you the exact formula for that. Now, then you can directly solve questions, don't worry. This is the middle level. This is the Fermi level. Intrinsic for intrinsic semiconductor. Then this is remember that formula. Okay, just slightly above the middle energy level, that is the EC plus CV by 2. This is the gap. This gap is given by KT by 2 log or NV by NC. NV by NC. This is for intrinsic semiconductor, just intrinsic semiconductor, guys. Okay then. Now, up to this point, any doubt? Anyone, any doubt? जल्दी से बताओ भाई, डाउट है तो बोलो जरा, एनी डाउट? हेलो, हाँ, EC प्लस CV बाई 2 प्लस KT बाई 2 लॉग ऑफ NV बाई NC हो गया ये. अब देखते हैं जरा दूसरा. द नेक्स्ट वन इज, अब जैसे आप देखोगे ना, फॉर एन टाइप सेमीकंडक्टर, दिस इज फॉर एन टाइप सेमीकंडक्टर. इन एन टाइप सेमीकंडक्टर इज फर्मी लेवल इज नियर टू व्हाट? Near to conduction band. Near to what? Conduction band. No doubt abhi this point, NV also depends upon the temperature. How? I will give you the exact formula for NV and NC. But first of all, Fermi level for n-type semiconductor, it is near to what? Conduction band. Near to conduction band means, this is, for example, it is the intrinsic Fermi level. EFI. Okay, and this is the EC. So what is the gap EC minus EF? And what is the gap EF minus EFI? EF minus EFI. You have to calculate this, right? Then EF minus EFI depends upon what? Ni. So that is given by KT log of, आपने डोपिंग क्या की? ND by Ni. ND by Ni. Intrinsic carrier concentration, ND is the actual doping. ND is what we are actually giving the doping, ND. Right, so that is the gap. Or EC minus EF, if suppose you have to calculate the EC minus EF, this gap, then this is given by KT log of NC by N. What is the actual concentration of electron and what is the standard density of what state here? Accordingly we can find, or normally N is nearly equal to what? ND. Here N is nearly equal to what? ND. You can put ND here. In place of N you can put the ND. So KT log. So that is the gap. EC minus EF, what is the gap? And EF minus EFI, what is the gap? So what is the question? What is asked in question? Be careful about this. समझ में आ रहा है ये आपको? ये आया आपको समझ में? ये आ गया ना? Then characteristics of the Fermi level in n-type semiconductor. What is the characteristics of Fermi level? So this is the Fermi level, what is the gap and so on. That type of questions they will ask, right? And what are the characteristics? As you know, probability क्या है आपका exactly at Fermi energy level, what is the probability of finding an electron? So we are getting questions based on this. So one student asked, what is the formula, sir, here? So this is the formula. temperature dependence of intrinsic concentration. First of all, intrinsic carrier concentration is given by Ni square is equal to, so watch this, the probability of finding electron above the Fermi level is 0 now. No. The probability of finding electron above the Fermi level is 0 under what? 0 degree Kelvin. 0 degree Kelvin means at 0 degree Kelvin, what about the number of electron or concentration of electron in conduction band? 0. And it is 1 in what? Valence band, because all the electrons will be in valence band. But if we are increasing the temperature, then what will happen? Conduction band concentration of electron will increase. That's why the probability of finding an electron will also increase. So that is the case. Now that is the intrinsic carrier concentration, A naught T cube e raised to power minus Eg 0 by kT. Then this is the case. A naught is the constant. That constant is given by this formula. Okay, that is the value. But only this is required here. Then mobility also depends upon the temperature. What is the mobility? T raised to power minus m. T raised to power, it is depends upon the mu is proportional to T raised to power minus m. And what is the value of the m here? 2.5 or 2.7, 1.33, 2.66. It is for what? Both germanium or what? For silicon. No need to mug up. They will provide you the data for this. They will provide you the, normally we are taking what 3 by 2. Now in between we are taking the 3 by 2 values. Then now any doubt regarding what Fermi level, guys? Any doubt regarding the Fermi level? Is it clear? So what will happen? They will ask few questions. So just I can conclude it. Always remember, first you can draw this diagram. This is the EC plus, this is the EI. This is the Fermi level for N type. This is the gap, right? KT log of, already I have given. This gap is what? NC by ND. Remember, this gap is KT log of ND by NI. Okay, that is important. But in P type, it is EC, it is EV, it is EFI. Now this is the EFP. This is what? EFP. Then this gap, EFP minus EV, is given by KT log of Na by P. P is nearly equal to what? NV. यह है NV by P. NV by P. And then this gap, KT log of Na upon Ni, where Na is actually concentration of what? Holes. Concentration of holes, guys. So yes, you can solve this question. So in P type, Fermi level is going downward. In N type, the Fermi level is going upward. Above the intrinsic Fermi level, below the intrinsic Fermi level. Normally we are getting the same type of question. Solve the previous year question, you will get the idea, right? I think you have solved number of questions on this. Yes, this is a quick revision. I will give you the idea. We will solve one more question on that. Now guys, before solving the question, quick revision of drift current. What is the drift current density? Drift current, there are two currents, drift and what? Diffusion. Drift means under the influence of what? Electric field, guys. and that drift current density is given by J is equal to what? Sigma E. J is equal to sigma E. J is given by NQ mu N plus PQ mu P into what? E. So this is the drift current density. J is given by I by A and so on under the influence of external electric field. And in this case, we are having the uniform doping. Uniform doping of electrons or uniform doping of holes. Okay. Now, what is the important? That is possible in case of semiconductor as well as in case of what? Conductor. Because when we are giving the electric field, under the influence of electric field, the charge carrier will move and there will be the current, and that is called drift current density. Now, when I am writing this formula, so what is the drift velocity? It is proportional to E, and the constant of proportionality is called mu E. Proportional Vd into what? Mu E. Mu E means what? Mu is the mobility, E is the electric field. What is the Vd? Vd is the drift velocity. So Vd is proportional to what? E. And now mobility also depends upon the temperature, guys. Temperature will affect the mobility. When we are talking about the room temperature, temperature increases, mobility decreases. Temperature increases, mobility decreases. Now, this is the drift current. Then, there is a diffusion current, guys. Diffusion current means when there is a concentration gradient. Concentration gradient means at one side there is a large concentration is very, very high, and other side the concentration is very low. Then the charge particle will move from higher concentration to lower concentration, and that phenomena is called what? Diffusion phenomena. And it is possible in case of what? It is possible in case of semiconductor only, not in case of conductor, because conductor concentration is uniform. But in case of semiconductor, what we can do? We can give the doping, or we can change the doping, non-uniform doping. For example, when we are moving from this point to this point, we can reduce the doping. When we are reducing the doping concentration of charge particle will also reduce. At this point, we have the large electron concentration. Here it is a less. The electron will move from higher concentration to lower, and hole will move from higher concentration to lower. Okay, and that is called what? Diffusion phenomena. But remember, because the charge of electron is negative, when the electron is moving from higher concentration to lower, current will move in opposite direction. Current will move in opposite direction in case of what? Electron. Or in case of hole, when this is the hole will move from higher concentration to lower concentration, and the current will also move in the same direction. So guys, when we are solving question, so conceptually, accordingly, you have to adjust the sign here. Sign means, for example, this is the x direction. This is the positive x direction. Tell me, this is the concentration of electron is 100 here, and concentration of electron is 10 here. So what about the current? Positive or negative? I want to calculate the current in positive x direction. Then what about the final current? Positive or negative? Tell me, with respect to what? Positive x direction. So that is the concentration of electron is 100 here, concentration of electron is 10 here. The electron will move from higher concentration to lower concentration. But actually the current is what? Move from lower to higher in negative x direction, and that's why we are getting the negative current. Negative current. Okay. Similarly, suppose it is hole. It is hole here 100, here 10. So hole will move from higher concentration to lower concentration, and current will also move in the same direction, in positive x direction. That's why we are getting the positive current here. Positive current or positive current density. So according to this, you can choose whether it is a positive or negative, because we are getting number of questions on that. Now, what about the formula here? In the formula, current density, because of hole, it is given by minus q dp by dx. dP is the diffusion constant or diffusion coefficient, and dP by dx is the concentration gradient, guys. Concentration gradient means, for example, here the P1 is 100, here the P2 is 10, and the distance between these two, that x2 is, it is given 11, x1 is given 1 here, 1 centimeter, 11 centimeter. So what is the concentration gradient? This is nothing but slope, P2 minus P1 upon x2 minus x1. P2 minus P1 upon x2 minus x1. So it will become 10 minus 100 upon 11 minus 1. And you will get the negative value. You will get the negative value. Okay. Now this negative and this negative will become positive. And we are getting the positive current. Yes. Hole will move from higher concentration to lower means in positive x direction, and current should be positive. So from the formula you should get the positive value of the current. That is the direction of the current in positive x direction. That's why we are putting the negative sign here. So this negative and this negative will become positive and you will get the positive answer. But in numerical you have to use the concept also. Na? Sometimes वो क्या होता है ना, formula में we are making silly mistakes in formula. So remember that. You know, we are getting the positive current. Similarly, in case of electron, that current density is given by, it is a positive q dn. Dn is the diffusion constant, dn by dx. You will get the dn by dx positive here. Positive or negative? N2 minus N1 upon x2 minus x1. Again the N2 is what? 10, N1 is 100, x2 is 11 minus 1. You will get the negative value. When we are putting this negative value, you will get the J negative. What is the meaning of the negative? Meaning of the negative is electron is moving from higher concentration to lower concentration, but current will be in opposite direction. Current will be in opposite direction, and that's why in this formula there is no negative sign, but in the formula of hole there is a negative sign. But some students are confused with the Q. Sir, charge of electron is negative. So what should be the value of Q here? Negative or positive? Guys, remember Q is simply 1.6 into 10 raised to power minus 19. Finished. Sometimes in Q or E we are using. So both are. No need to put the negative value because this is the formula for the electron. That's why we are putting the negative. No. Simply it is a charge. 1.6 into 10 raised to power minus 19 coulomb. Positive value, and from the given information you have to find the concentration gradient. Dn is the diffusion constant. In numerical they will provide you the diffusion constant, guys. Okay, so that is the value. Otherwise from Einstein equation you can find the diffusion constant. I think no doubt, because these two formulas are very very important one. यहां से आते ही हैं भाई क्वेश्चन करंट डेंसिटी से. चलिए अब आगे बढ़ते हैं. नाउ ये है डिफ्यूजन फिनोमिना. हायर कंसंट्रेशन टू लोअर कंसंट्रेशन होल, then electrons are moving here. Already I have given you the formula, diffusion current density. These are in a systematic manner. This formula is given. Here it is a negative sign. Sometimes we are making the silly mistake also. Q dn, dn by dx minus Q dp, dp by dx. Carrier lifetime. What is the carrier lifetime? Okay. So carrier lifetime is what? The time left by the charge carrier between generation and recombination. It is called mean lifetime between generation and what? Recombination. It is normally, it is in the range of from microsecond to what? Nanoseconds. Average time it takes for minority carrier to recombine. That is the definition. And we can find the lifetime by one method. What is the name of that method? Any idea how we can find the lifetime of charge carrier? In my classes already I have explained carrier lifetime and so on. There is a relation between diffusion length and carrier lifetime. Then I think you have idea about the pulse light method. Just this is the zero level. and this is a semiconductor bar. If you want to find the carrier lifetime, then first of all give the radiation here. When we are giving the radiation, concentration will increase. Concentration of charged particle will increase. Minority charge carrier will increase like this. For example, initially it is a minority charge carrier concentration, and now it is a 0 level. Then first of all, switch on the light. At this point, switch on the light. Concentration will increase and finally it will saturate. And at this point, switch off the light. Automatically this will start decreasing because of the recombination. And from that you can find what? Concentration of, mean lifetime of charge carrier. When it is exponentially decreasing, this is the time, right? Just switch on the light. Because of that, new hole electron pair will generate, but after some time it will saturate. Once it will saturate, now switch off the light. Because of the recombination, again concentration will start decreasing. It is a n-type bar. N-type bar, n is equal to nd. What is the concentration of hole? This is given by Ni square by nd. This is thermally generated charge carrier. This is the concentration of hole, Pn naught. Now, when we are giving the light, concentration of hole will increase and it will reach up to what maximum? This is called excess hole concentration. Exactly at t equal to 0. This is the excess hole concentration, and this is the, what is the total hole concentration? P naught. Now, at this point, this will remain constant, but this will decrease exponentially, T by tau P. And this is the total concentration of hole, and that is the function of time. And this is the time scale. And this is the tau P is called what? Mean lifetime of holes. And that method is called pulse light method. Pulse light method. Okay, Pn naught, you can find the Pn naught from what? This formula, mass action law. This will remain same, but excess hole concentration will start reducing. From that you can find. So sometimes there may be the chance they will give you this type of diagram, and from the diagram you have to find what mean lifetime. Otherwise, if you have the idea about the diffusion length, the diffusion length is the average distance that excess carrier can cover before they recombine. Means what is the mean distance covered by the charged particle between generation and recombination? That is called what? Diffusion length. And what is the relation between the diffusion length and mean lifetime? The diffusion length is given by d tau. Tau is the mean lifetime, d is the diffusion coefficient, guys. So for holes, root over dp tau p. For electron, root over dn tau n. Tau n is the mean lifetime of electron and dp is the diffusion coefficient, guys. Okay, then what is the Einstein relation? Einstein relation, because number of numericals you have to find a value. Suppose in some numerical diffusion coefficient is not given. So dn by mu n is equal to dp by mu p is equal to Vt. Vt is the volt equivalent of temperature. That is called kT by Q. And as you know, Vt is given by 0.0259, or normally it is called 0.026 volt or 26 millivolt at 300 degree Kelvin, or it is 25 millivolt at 25 degree centigrade or 298 degree Kelvin. Okay, so this is the kT by Q. kT by Q is nothing but T by 11,600. T by 11,600. So this is the Einstein equation. In numericals, we have to use Einstein equation. Yes, 26 millivolt at 300 degree Kelvin or 25 millivolt at 25 degree centigrade or 298 degree Kelvin. 298 degree Kelvin, guys. Okay. Okay, then, so up to this point, Einstein equation, you have idea. Then, what is the relation between the mobility and what that temperature and so on? Tell me, up to this point, any doubt? Up to this point, any doubt? Anyone? कोई भी चीज़ है पूछ सकते हो आप लोग. थोड़ा रुकना पड़ेगा भाई, ये क्लास अभी जाएगी 7:30 PM तक. इट इज़ अ क्विक रिवीजन। ये नहीं बोल सकते कि आप एकदम ही आपको कुछ पता नहीं है तो आपको आ जाएगा, क्योंकि देखो ईडीसी बहुत ही लेंथी सब्जेक्ट है ना। तो जल्दी से बताइए ज़रा क्या होगा। चलो बोलो ज़रा, कोई भी डाउट है तो पूछिए, मैं आपको 2 मिनट दे रहा हूँ भाई। यहाँ तक सर, how much marks we can score easily in this subject? It depends on you guys. They visit what sir, every year they ask new type of questions from this subject. One or two questions we are getting extraordinary questions from this subject. But last year, Vikram, watch the last year paper 2023. Straightforward formula based question. Early क्या नाम है उससे, last year in 2022 there was a one question based on what continuity equations. So if it is a very lengthy question or it will take time, to simply leave it. But if it is MSQ, try to understand. If it is a MSQ, you have to attempt. Why? Because there is no negative marking. Second, if it is a numerical answer type question, again you have to attempt because there is no negative marking. Or sometimes they are giving extraordinary questions. So marks to all type of questions we are getting. Yes, last year that was the question, marks to all, because there was some problem. So don't waste your time. Don't waste your time during exam. In one attempt, you are getting idea. Yes, that is the method to solve the question, solve it. Otherwise, simply leave it. Okay, don't waste because it is very important. Smart approach. If it is MSQ, attempt. Because there is no negative marking, a numerical answer type question, one attempt, you get the answer, please put the answer. Because there is no negative marking. But in case of MCQ, take care. Okay? Yes, it is a lengthy question, but if you want to get the top rank, guys, you have to prepare all the subjects. Suppose you are getting the question on very basics, then just formula based question. Yes, it is possible. We are getting formula based question. Sometimes they will give what, 8 marks, sometimes up to 15 marks from EDC. Why? Because it is a core subject of what, electronics and telecommunication. Okay, no doubt. I am audible. I'm audible, na? Okay then. Then next, Einstein equation. Then Hall effect. Sometimes we are getting questions on what, Hall effect. From this, we can find whether the semiconductor is p-type or n-type. First thing. Second, we are getting the concentration N or P. What is the value of the N? What is the value of the P? If it is p-type, then what is the P concentration we can find? As well as we can find the mobility of majority charge carriers, not the minority charge carrier. We can find the, if it is n-type, then what is the mobility of electron? If it is p-type, then what is the mobility of holes? We can find, guys. Okay, that is the Hall effect. Right now it is called a Hall. We are providing electric current in x direction, magnetic field in what? Z direction. And because of Fleming's left hand rule, this is the Fleming's left hand rule. Current in x direction, this is the father, mother, children. Current in x direction, magnetic, right, and then what? Magnetic field outside the page, and then force will be downward direction. Force will be in the downward direction, guys. So you can also use the concept of EMFT here, and then when there is a force in the downward direction, if it is p type, then hole will be collected. If hole will be collected, then it is called what? P type. If the if electron is collected on the lower plate, then it will become what? N type semiconductor, we can say, right? So this is or under equilibrium, the force due to what? That force due to the charge carrier because of the electric field and force due to what? Magnetic will become equal. So this is the what will happen once the hole is collected downward. There is a negative charge with respect to that. This plate will become negative, that will become positive, and there will be one electric field. What is the, where is the electric field? In what? From positive to negative direction. This is called direction of the electric field. Now, because of the magnetic field, hole will move downward, and because of this electric field, hole will try to move upward. Why? Because it is the electric field, and what is the force? QE in case of hole. That is in upward direction, and because of that magnetic field, that is in the downward direction, guys. So that is a very, very important concept here. Okay. So that these two forces will nullify each other. So under equilibrium, both are equal, and accordingly we can find the formula here, guys. Now this is the D, this is the W width here. This is also very important, and that is the D, distance between the plates. WD. That what is the cross sectional area? W into D. Cross sectional area, why it is important? Because what is the current density? J, I by A. Current density, that is the J, that is I by A, or that is given by sigma E. N Q mu N into what? E. But this E, when I am talking about this E, that is in horizontal direction. That is in what? Horizontal direction. Remember, we are providing the electric field, but it is not mentioned in the board, but actually we are providing, and because of that electric field, there is a current in x direction I. X direction I, we are just connecting a battery, and that will create electric field in horizontal direction, and there is a current through the conductor. Whether it is a semiconductor N type or P type, current will be in the same direction I, right? And we have the resistance of this bar. Resistance is given by rho L by A. What is the rho? Resistivity. L is the length of the bar, A is the area of cross section. Then 1 by sigma L by A. Or resistance is what? V by I. So from this you can find the resistance V by I. From resistance you can find the conductivity sigma. Because L is known, A is known, you can find what? Sigma. Once the sigma is known, so what is the sigma here? N Q mu N. And if you have the concentration, you have the value of the Q, then you can find the mobility. You can find the mobility of charge particle. So these are the formula. These are the important formula for Hall effect, guys. Now there are, I am just concluding the formula here. First, you have to equate the two forces. One is called force because of the magnetic field, one is called force because of the electric field. Equate these two. This is in vertical direction. This is in what? Vertical direction, right? And now this is the drift velocity of charge particle. Drift velocity of what? Charge particle. That is V. Okay. Then what? J. I by A is given by sigma E. Sigma E is what? N Q mu N because of electron E. This mu N into E is called drift velocity, and Q is called volume charge density. I by A is equal to what? This is called volume charge density rho, and mu N into E is called V. What is the drift velocity? I by A rho. I by A, what is the A? W into D into rho. Rho is the volume charge density. You can put this value here. This Q is cancel out. You can put V I by W D rho is equal to E. What is the E? Hall voltage upon what? D. Because Hall voltage is developed between these two plates, and D is the distance between these two plates, and that is called VH by D. That is the value of the electric field in vertical direction. Then guys, this D is cancel out, and what is the Hall voltage? B I by W rho. B I by W rho. Q N Q is rho. I think not is clear to you. NQ is rho, and 1 by rho is called Hall coefficient. 1 by rho is called Hall coefficient, guys. So what is the value of the Hall coefficient? VH into W upon VI. VH into W upon VI. Okay, so these are the important formula. So why I have given this derivation? Because sometimes what will happen? They will change the data, right? Or they will change the orientation. They will put the W in place of D or D in place of W. Then that will create what? Confusion. So what is the D and what is the W? You have to take care of that. Hall voltage positive for P type, negative for N type. Vikram, what? वो भी ना Vikram देखो. That depends upon the applied voltage. So don't try to mug up. Suppose we are calculating voltage with respect to what? Plate number 1 is the downward plate, 2 is the upward plate. Then yes, your answer is correct. VH is positive for P type, VH is negative for N type. But suppose we are changing the polarity of the voltmeter, then what will happen? Opposite. By default, that is the value. Now, तो Hall effect का significance क्या है? With the help of Hall effect, first thing, you can find whether it is N type or P type. You can find the mobility. You can use this formula, right? So these are the important formula, guys. VH, then RH. Once you have the RH means once you have the RH means what? You have the rho. NQ, and you have resistance rho L by A, 1 by sigma L by A. What is the conductivity? Conductivity is equal to 1 by RA or L by RA. R is the resistance. How we can find the resistance? V upon I. Then once you have the sigma, what is the sigma here? NQ mu N. NQ is nothing but rho mu N. Rho is the volume charge density, mu N upon RH. What is the mobility? Sigma RH. So these all are the important formulas. These all are the important formula related to Hall effect. Straightforward question on Hall effect. That is important. Mu N is equal to sigma times of RH. But you have to find the sigma from this. Otherwise, they will provide you the sigma. This R is resistance actually. RH means what? Hall coefficient. RH means Hall coefficient. This rho is the what? Resistivity, and this rho is what? Volume charge density. This rho is volume charge density. We are using the same formula, but yes, that is the case. So what are the significance of Hall effect? That is given. We can identify whether the semiconductor for N type Hall voltage is positive and for P type Hall voltage is negative. For example, it is given. What about this statement? You can say, sir, it is wrong. वो डिपेंड करता है, तो इस स्टेटमेंट को मैं जनरलाइज नहीं करूंगा. Why generalize नहीं? Because where we are going to check, where we are going to calculate the voltage between which plates, So sometimes positive for p type, negative for what? N type. So that depends upon the polarity of voltmeter. It is used to determine Hall voltage, Hall current, Hall coefficient, conductivity. We can measure the carrier concentration. We can measure the mobility of charge carrier. We can measure the magnetic flux density. Yes. We can also measure the magnetic flux density B. You can find. This concept is used in what? Magnetic field meter. Magnetic field meter. And you can also use it for what? Multiplication of the signal. Multiplier. This is called Hall effect multiplier. We can use it. Now, next one is continuity equation. Continuity equation. Last time we have one question on the continuity equation. On my YouTube, I have solved that question. So you can go through that. You can understand how we can solve the question. Find the link. 2022 gate paper or 2023 gate paper. I have solved all the questions from EDC. And solve that question on continuity equation. That is a previous year question. But remember, continuity equation means what? It is based on law of conservation of charge. Law of conservation of charge means charge can neither be created nor be destroyed. So that is the one formula. This is that will relate the space and time. This means distance and time. So dN by dt, that is the rate of change of the concentration, is 1 by q. dJn by dx, this is the with respect to distance, plus generation rate of the electron minus generation recombination rate. That is the formula continuity equation. So if any information is given about the Jn, you can differentiate with respect to x and you can find this value dJn by dx, and then you can use this equation and you can find what is the rate of change of concentration of electron. And similarly, dP by dt is given by minus 1 by q dJp by dx plus generation rate of electron holes and minus recombination. This is the generation rate, this is the recombination rate, guys. This is the minus 1 by q dJp by dx. Remember these two formula. And then, as you know, Jn. What is the electron? What is the drift plus diffusion current density? Drift plus diffusion current density. NQ mu n into E, this is the drift current density, plus what? Q dN by dx. This is the diffusion current density. Now differentiate it with respect to what? X. Differentiate with respect to X. So there are two variables, guys. In this case, N is a variable, E is also variable. So when I am differentiating, you will get N Q mu n d by dx. I am taking N as a constant. Second time I am taking E as a constant. So it will become Q mu n E dN by dx. Right. And when I am differentiating, this is the double differentiation. Q dN d square n by dx square. Now what I want to say, put this formula in place of dJn by dx. When I am putting that formula in case of dJn by dx, you will get this one. Q cancel out, 1 by q, because of that q is common, constant, cancel out. You will get n mu n d by dx, mu n into E dN by dx, plus dN because q is cancel out, d square n by dx square, plus generation rate minus recombination, and that is the formula. So बताइए अब easy है ये? That is not easy. Was the extraordinary question, and Vikram I have solved. But in exam hall, no need to solve those type of questions because it will waste your time. If you have the sufficient time, you are able to solve, then okay. Otherwise, simply leave it. Right. Just remember time management, guys. Similarly, for electron, what is the current density? Drift plus diffusion is given by PQ mu P into E minus Q dP by dx. Differentiate it, find the dJp by dx, put here, and you will get this formula. You will get this formula. Okay then. Direct, sometimes we are getting a straightforward question on this. So yes, now indirect band gap semiconductor and direct band gap semiconductor. So that is the continuity equation. So please note that those points. Indirect or direct band gap means what? EK diagram. That is what momentum here. EK. This is called EK diagram. Here, when the electron falls from conduction band to what valence band, there is no change in momentum, and directly electron will recombine with the holes, and it will give the energy in the form of what? Light. But in this case, what will happen? Suppose this is the EK diagram. What about this is the electron in the conduction band and that is the hole in the valence band? They have the different K. That's why it is called indirect band gap. First of all, we are having the defected state here, and then same K, and then it will recombine with the holes. So that it will give energy in the form of what? Heat. For example, germanium and silicon are of indirect band gap semiconductor. And direct band gap semiconductor means gallium arsenide and so on. Okay, so these are the case: direct band gap and indirect band gap. Sometimes in theory book it is given after defected state. This is called defected state. It will give the, because now it is a direct band from this point of view, it will give the very small amount of energy in the form of what? Light also. But that is insufficient, insignificant also. Now this heat, what will happen? Because of this heat, the temperature of lattice structure will increase, and because of this we are getting the light. That is the concept of what? Light emitting diode. So this is called EK diagram, direct band gap and indirect band gap semiconductor. Now which type of questions we can assume, guys? Just for example, this is the question: the band gap of silicon at 300 degree Kelvin. In 2003, 1 mark question, very easy question. In last 20 to 23 years question. So initially they have asked what? Very easy question: the band gap of silicon at 300 degree Kelvin. What is the answer here? That is all are nearby 1.16, 1.10, 0.80, 0.67. What is the answer for this question? Band gap of silicon at 300 degree Kelvin. Okay, B, very easy, 1.10. 1.21 is at 0 degree Kelvin, right? And then that is the question on what? The resistivity of uniformly doped n-type sample is 0.5. If the electron mobility is and the charge of the electron is, the donor impurity concentration Nd in the sample is. Donor impurity. Are you getting this question? Resistivity is given. So as you know, conductivity is equal to what? 1 by resistivity. And it is given by N Q mu n into E. And now resistivity is given, you can find the conductivity, electron mobility is given, charge of the electron is given, the donor impurity concentration Nd you have to find. Then, oh, not E, sorry, E is extra here, no. So N is nearly equal to what? Nd. What is this? Okay, khatam. Resistivity, Q, mobility, all are given. Resistivity is given, Q is given, mu n is given. You can find the N is equal to N2. Can you find? Can you find this value? Very easy. Okay, then formula based question. Then this is just I am giving you the basic idea, right? Silicon sample A is doped with this one, boron. Another sample B of the identical dimension is doped with the atom of phosphorus. Boron is what? Trivalent, means it is a p type. What is the same? Phosphorus means it is a n type. Phosphorus is a pentavalent. The ratio of the electron to hole mobility is 3. So mu n by mu p is 3. Ratio of the conductivity of the sample A to B is opposite. A to B is what? Opposite, because it is what? P type. It is a P type. So what is the sigma? P Q mu P. A. What is the sigma B? N Q mu N. You have to avoid the silly mistakes, guys. And both are equal. P or N are equal because P is equal to Na. or n is equal to nd, both are equal, that's why this is cancel out. Sigma a by sigma b, nothing but mu p by mu n, 1 by 3. So this is a 2-mark question, right? 1 by 3, and that is the case. To conductivity, so that was the question I have asked now. In case of intrinsic semiconductor, if both the same, then the conductivity is mainly due to what? The conductivity is mainly due to holes. Then guys, next one. So this type of questions we are getting. In Fermi level, we are getting this type of questions. Silicon is doped with boron. Boron means what? Trivalent, having the concentration. Assuming the intrinsic concentration is this much. Thermal voltage is given. Compared to undoped silicon, the Fermi level of doped silicon. So boron means what? It is a p-type. Boron means trivalent. It is a Na. Once it is a p-type. When it is a p-type semiconductor, means Fermi level is going downward. So directly on question, get the key points. Downward means this is the EC. This is the Fermi level. This is the EV. Where is the Fermi level? This is the Fermi level, EFP. Going downward. And what is this gap? KT log of Na by Ni. KT log of Na by Ni. Is it clear? तो बताइए जरा क्या होगा, क्या है आंसर? Tell me what is the answer for this question. Okay, which answer is correct? C. Yes, Vikram. Now it is goes down and goes down by what? 0.42. That is the KT log of Na by Na. KT means what? VT. You can directly use this 0.25. That is in energy, in the form of energy, 0.025. This is the value of the KT log of. Na means boron concentration. What is the concentration? 4 into 10 raised to power 17. And now Ni. Ni it is given in the question, no? What is the Ni given? 1.5 into 10 raised to power 10. Use your virtual calculator and solve and you will get the answer. You will get this answer C. So this type of questions they are asking. So then goes down by this one value. Then guys, next one. So I think now it is clear to you Fermi level which type of questions they will ask. And now N-type semiconductor Fermi level is given. Again it is a homework for you. Try to solve this type of questions. In previous year question you will get the idea. And after that you can also give the quiz. Now guys, this is all about what? P-type semiconductor. Now we will enter into what? PN junction. Quickly we will cover PN junction and what? Then PN junction and then what? BJT. And then after that we will cover MOS capacitor, MOSFET and what? Very very important topic, that is special diodes. So till then please try to solve this question and give me the answer for this one. That is not a homework. Please take a screenshot. Just I am giving you the 15 minutes break here because it's a long marathon session. Try to solve, take a screenshot of this, and then just after that, and that was the question in ISRO examination, guys. Similar type of question in ISRO examination, we can expect this type of questions in GATE. It is in ISRO 2020. So this is also, try to solve this question. This is take a screenshot of that. And now okay then. तो कोई क्लास नहीं छोड़ना. I will also cover the special diodes. Please don't leave the class. Just after 15 minutes and ask your friends to join the session also. Okay? Okay then. Thank you. अभी जाइएगा नहीं. अभी ये कंटिन्यू रहेगी क्लास. 15 मिनट्स में वापस मिलते हैं हम लोग. फिर से आते हैं और फिर कंटिन्यू करेंगे इसे. page we are going to start what PN junction and as well as what BJT. Okay, now quickly. Okay, what is the problem here? Now, so I think you have solved this question in within 15 minutes break, right? So in a semiconductor device, if the Fermi level is positioned at conduction band EC, मतलब EC and EF are at the same level, determine the approximate probability of finding electron in state EC plus EF. Oh, there was a misprint because of that, right? Then where K is the Boltzmann constant and T is the device, this is the EC plus EF. Okay then. Now, so this is the assignment and try to solve this question. Then at the end I will solve. At the end I will solve this question. Up to this point, any doubt regarding Fermi level semiconductor physics? Okay then. Next one, PN junction, guys. PN junction means in a diode that there are application of what diode, that is rectifier, clipper, clamper, voltage doubler, peak detector, precision rectifier. Okay, so these all are the applications of the diode and that is the part of what analog. Here we will learn about the PN junction. What about the built-in potential, law of junction, right, and current components and so on. Now it is a PN junction. Depletion layer established on both the sides of the junction. Barrier potential is developed across the junction. Formation of the PN junction and diffusion capacitance. Then that is the, for example, this is the PN junction. Watch this. This is the PN junction, P type, N type. It is a metallurgical junction. It is just not a physical junction. It is a metallurgical junction. Here we are having the negative ions. These are called acceptor ions. And here we are having the positive ions. There is no mobile charge carrier, no electron, no holes. Here we are having the holes. Here we are having the electrons. Right, here holes, here what? Electrons, negative charge and what? Positive charge, and that region is called space charge region. Now watch the direction. What will be the question? What is the direction of the electric field from positive charge to negative charge? That is the direction of the electric field. It will stop the flow of the holes because the concentration of hole at this region is very high. This is the, we are giving the Na doping, that's why the concentration of hole is very high. Here the concentration of electron is very high, that's why the hole will move from higher concentration to lower concentration. Then there is a establishment of electric field in depletion layer, and this electric field will exert a force in opposite direction, means it want to stop the diffusion of the holes. Similarly, this electric field will exert the force in this X direction so that it will stop the diffusion of what? Electron. And in open circuit bar, what will be the total current? Zero. Drift plus diffusion current is what? Zero. And because of that, there is a built-in potential. That built-in potential is given by Vt log of Na Nd by Ni square. Na Nd by Ni square, guys. तो कई लोगों को डाउट होता है ना, सर इलेक्ट्रिक फील्ड कैसे डेवलप हो गई? तो दैट इज द इलेक्ट्रिक फील्ड बिकॉज ऑफ व्हाट? दिस immobile charge carriers only. Uncovered immobile charge carrier. These are called covered mobile charge carriers. And always remember, this area is neutral. This area is neutral. This area is neutral. So only the electric field will be in this region. In space charge region, transition region, and so on. The number of questions based on what? Transition region, guys. Okay then. Next one. Next. The first formula is here, built-in potential. Then watch this. So always remember, if the Na is equal to Nd, then depletion within P side and depletion within N side are equal. But if the Na is greater than Nd, then depletion width on the P side is less than the depletion width on the N side. If the Na is less than Nd, depletion width on N side is less than or depletion width on the P side, guys. Means what is the constant here? Na into Wp is equal to Nd into Wn. This is the formula. More will be the concentration, doping concentration, less will be the depletion width. So tell me for this diagram. Tell me for this diagram, which one is correct? Na equal to Nd, Na less than Nd, or Na greater than Nd? Which is correct for this particular diagram? Here it is a immobile charge acceptor ion, hole is connected, this area is neutral, this area is also neutral. Here, right, this is the depletion layer, you can remove this. Only the acceptor ions. This is the depletion width on the N side, and this is the depletion width on the P side, right? And uniform doping. Uniform doping. Yes, Na is greater than Nd. Uniform, when we are using the uniform doping, so some students are confused. Sir, one side it is what? Na, one side Nd. How you can say uniform doping? If there is a uniform doping, means there is no diffusion. But what is the meaning of the uniform doping? Here Na is uniform. Suppose when we are talking about the Na, Na is what? Uniform. So that is the Na. Concentration of electron hole is uniform in this region. In P region it is uniform doping. But in N region, N is equal to what? Nd. And what is the P in N region? Ni square by Nd according to mass action law. This is very, very less. So suddenly it will reduce. And again it is uniform. In N region it is uniform, in P region uniform, and there is a step grading. This is called step graded semiconductor. So what is the concentration of hole in this region? Na, very, very large. And what is the concentration of hole here? Pn naught, very small. Minority charge carrier. There is a step grading. But in this region it is uniform, in this region it is uniform. That is called what? Uniform doping, step graded. And sometimes linearly graded means what? Linearly graded means, suppose this is a bar. Now the concentration will reduce. From this point to this point. Okay, that is the concentration decreases. P1 and P2. Now that is the case, guys. P1 and P2, this is called linearly graded. At this point concentration is high, at this point concentration is low. That type of semiconductor is called what? Linearly graded semiconductor. So we are having two types. That is the step graded and linearly graded junctions. In both the cases, hole will diffuse from higher concentration to what? Lower concentration. And to stop this diffusion, electric field will establish, and that will cause what? Drift current. Drift plus diffusion will become zero. That is a very simple explanation of this. Now, in both the cases, what will happen? Because of this space charge region, when we are making more and more reverse bias, suppose we are giving more and more reverse bias, then hole will move away from the junction. Electron will move away from the junction. Width of the junction increases because of the reverse biasing. When the width of the junction increases, concentration of the immobile charge carrier will change, And always remember, if there is a change in charge because of the change in voltage, means there is a capacitance. Change in charge because of the change in voltage. So in the reverse direction, always remember, when we are increasing the voltage in reverse direction, depletion width will increase. This is called reverse bias PN junction. ये तो बहुत ही simple है, ये आपको सबको पता है, VR. This is the reverse bias. P is connected to negative, R is connected, N is connected to positive. When we are making reverse bias, it will increase the reverse. Now, because of that, okay, everyone, very good afternoon. And अभी थोड़ा आपका त्योहार भी गया है, हैप्पी मकर संक्रांति. कुछ पतंग वगैरह उड़ा लीजिए आप लोग. Now, CT dq by dV, the depletion width will increase. Because of that, this capacitance will change. What is the name of the capacitance when the junction is reverse bias? What is the name of the capacitance? Now that number of questions on this capacitance, just quickly revision of the formula. First of all, that is given by change in charge because of change in voltage. W is the depletion width, epsilon S is the epsilon naught, epsilon R. Farad per centimeter. Okay, that is the value, minus 14 farad per centimeter. And then epsilon R for 11.7 for silicon, or sometimes in some books it is given as 12 for silicon, no problem. Epsilon R you can use. Now for W, you have to apply this formula Vj. Vj is nothing but V0 plus VR, voltage applied in reverse direction, and that is given by W square. Qn 2 epsilon W is depletion capacitance. Yes, transition layer capacitance, depletion capacitance. You can find the N 1 by Na plus 1 by Nd. Right, but remember, if Na is very greater than Nd, then this N will become Nd. And here W is Wp plus Wn. So when Na is very large, only Wn nearly equal to Wn. You can neglect the depletion width in N region, P region. Then this is the first case. Second case, Nd is very greater than Na. Wp nearly equal to Wp, guys. So that is the case. Remember, these are the two extreme cases, but if they are comparable means Na is nearly equal to Nd, then you have to use this formula, where V0 is the built-in potential, Vr is the voltage applied in the reverse direction, Qn by 2 epsilon S W square. From this formula you can say W is what? Proportional to root over Vj. Therefore, capacitance is inversely proportional to root over Vj, because Ct is proportional to 1 by W. From this formula, Ct is equal to epsilon naught A by W. So this is the case. So Vj. So number of times they will ask question. So always use this formula. Ct2 upon Ct1. Two different cases is equal to root over V0 plus VR1. This is the first case because it is inversely proportional. V0 plus VR2, that is the second case. They will give you the two conditions. In one condition, that is the VR applied voltage is this much, built-in potential is this much, and the value of the capacitance is this one. Now we are changing the reverse voltage, what will happen? So always use this formula, Ct2, Ct1 in second case, in first case, this is the first case, that is the second case. Why? Because it is inversely proportional, that's why we are using this formula. Now, from this directly you can find the answer for this particular question, or straightforward you can use, otherwise that is the formula you can use like that. That is what about the transition capacitance. Sometimes what will happen, reverse voltage, applied voltage, very greater than V naught, built-in potential, then you can neglect V naught. Or next thing, if the diode is forward bias, if it is forward bias, then Vj will become V naught minus what? Forward bias voltage. Minus. If it is a reverse bias, then it is a V naught plus Vr, or if it is a reverse bias, then it is a minus. It will reduce the potential barrier. It will reduce the potential barrier, guys. And that's why what will happen, when the Vj will reduce because of the forward bias, what about the capacitance? Increases. So logically, Vr increases. When the voltage in reverse direction increases, transition capacitance decreases. When the forward bias voltage increases, Vj decreases, and because of that Ct increases. Ct increases. In forward direction, we are having the more capacitance as compared to what? Reverse bias. So that is the case, guys. Okay. So number of questions on the transition capacitance. Then under ideal condition, what is the equation of the current? This is given by I naught e raised to power V by eta Vt minus 1. V is the applied voltage across the diode, and I is the current in this direction from P side to N side, and that is the relation I naught V by eta Vt minus 1. Eta is 1 for germanium, 2 for silicon. लेकिन समझना, दिस इज फॉर रेटेड करंट. कई बार क्या होता है, दे विल गिव यू द वेरी हाई करंट. This is for rated current. If you are giving the very high current, for example in ISRO there was the question, eta is 1 for germanium as well as for silicon for high current. So they will provide you the data and you can take a eta is what? Equal to 1. For example, in case of BJT. In case of BJT, whether it is a silicon BJT or germanium, we are using eta is equal to 1. So BJT is also we are having the junction. So that is the case. So for one for both higher level of current, and that is the operating condition, and that is the formula. Now what is the formula for the I naught? In EDC there was one question on I naught. It is called find the reverse saturation current and so on. Reverse saturation current means I naught is equal to, it is given by AQ dP Pn naught upon Lp plus AQDN NP naught upon Ln. That is the formula, guys. AQDP Pn naught upon Lp, AQDN NP naught upon Ln. This is the I naught, reverse saturation current. If any time current density is required, then remember I naught upon A. You can take A as a common, and I naught upon A will become reverse saturation current density. Okay, tell me, reverse saturation current for germanium, it is in which range? Milliampere, microampere or nanoampere? Normally for germanium, tell me. And guys, if you are enjoying the session, then like the session and ask your friend to join. Nanoampere. One is Tejaswini is giving the microampere. Okay. Array germanium, I am talking about the germanium. I am talking about the germanium, guys. For germanium, it is in the range of microampere, and for silicon, it is in the range of nanoampere. Yes, Srishti, your answer is correct. Your answer is correct. Now, so first of all, you have to use this formula in EDC. There was one question on reverse saturation current, and that is the formula for the reverse saturation current. And then you can use dP is the diffusion constant for hole, dN is the diffusion constant for electron. This is the diffusion length, this is the diffusion length, A is the area, Q is the charge, and Pn naught minority charge carrier. It depends upon the minority charge carrier, that is the hole in N side and P electron in P side. So minority charge carrier Pn naught is given by Ni square by Nd on N side, or Np naught is given by Ni square by Na in P side. This is a very important. It depends upon the minority charge carrier. Now, next one. Next is directly straightforward. You are getting this type of questions, guys. Then sometimes we are getting this type of questions, guys, about the diode. About diode means what? In the figure, silicon diode is carrying a constant current of 1 milliampere. When the temperature of the diode is 20 degrees centigrade, Vd is found to be 700 millivolt. If the temperature rises to 40 degrees centigrade, Vd become approximately equal to. What about the voltage across the diode? Voltage across the diode decreases as temperature increases. Voltage across the diode decreases means this coefficient is negative. In some book it is given 2.0 millivolt per degree centigrade. In some book it is given minus 2.5 millivolt per degree centigrade. In some numericals it is given minus 1.7 millivolt per degree centigrade. That is the case. So you can choose this value nearly equal to this value, around 2. So initially what is the voltage across that? Because current is constant. This current is constant. And that's why what is the drop? Vd is found to be 700 millivolt. Initially it is 0.7 volt. 0.7 volt. Exactly at what temperature? If the temperature increases to 40 degree, or initially the temperature is 20 degree. So what is the change in the temperature? 40 minus 20, that is the 20 degree centigrade. So what will be the change if you are taking this value? Then the change in Vd, that is also negative. 2 into 20 minus 40 means this will reduce by what? Minus 40 millivolt. So minus 700 minus 40, so 660 millivolt. 660 millivolt is the voltage drop across the diode. Straightforward, you can solve this type of question. So that is not the answer, it will not increase. That is not the answer, it will remain same. That is decreased by what? Only 10 millivolt per degree centigrade. That is not the correct. So this is the answer, B. B is the answer. So you can choose what? 2 or 2.5 or 1.7, nearly equal to, you will get the same answer from this type of questions. So when we are talking about the reverse saturation current, it doubles for every 10 degree rise in temperature. When we are talking about the drop across the diode, it will reduce by what? 2 millivolt per degree centigrade. So reverse saturation current if doubles, so this is the formula. At any temperature, T1 is given by, at T, 2 to the power T1 minus T upon 2. 10. For every 10 degree rise in temperature, it will increase by what? Double. Reverse saturation doubles for every 10 degree centigrade rise in temperature. So you can follow this formula. I naught T1, I naught T, 2 to the power T1 minus T by 10. Then, this is about the reverse saturation current. Before entering into the next topic, remember guys, take a step towards success in GATE National Scholarship Test. If you want to start your preparation for GATE 2025, 2026, then it is a golden opportunity for you guys. and please note the date on the, that is already it is done, but that window is open. You can also give the test from 9 a.m. to what 9 p.m. in coming Sunday. That is what in next Sunday. Okay, from 9 a.m. to 9 p.m. 90% off on our program, and that is the very important workshop by Rakesh Talreja sir on 17th of January, means tomorrow. 7 golden rules to get 2025 in first attempt. If you have any queries, any questions related to what your preparation, right, any hesitation, start करने में कोई problem आ रही है या आपको कोई doubts है regarding what gate examination, तो यहाँ आपको सब आंसर मिलेंगे. आप यहाँ आइए, वर्कशॉप अटेंड कीजिए एंड देन आस्क योर क्वेश्चंस गाइस. अब आप डिले मत कीजिए कि सर अब मैं सोच रहा हूँ मैं कब स्टार्ट करूँ, पता चला सोचते सोचते आपने 4-5 महीने बिता दिए. स्टार्ट करना है तो स्टार्ट योर प्रिपरेशन, और अगर आपको दिमाग में कोई क्वेश्चंस है तो यहाँ पर आकर आप क्वेश्चन जरूर पूछिए. और इन कमिंग संडे देयर विल बी द नेशनल स्कॉलरशिप टेस्ट, यू कैन ज्वाइन दैट टेस्ट गाइस ऑल्सो. ओके, तो ये इंपॉर्टेंट है आप लोगों के लिए. नाउ देन, तो अप टू दिस पॉइंट एनी डाउट? Sometimes देखो that sometimes we are getting a very good question, but it is only a 1 mark question on the characteristics, that is called piecewise linear model of the diode. That is a part of what EDC as well as part of what analog, it depends. But remember, for example, that is based on what IV characteristics of the diode in the circuit figure. V minus 0.7 upon 500, 0 ampere, the current in the circuit is. What is the answer for this question? So it is only of 1 marks in 2012, right guys? But number of students are here, sir कैसे बनाना है? देखो, simply apply the network here. Voltage, normally what we are assuming, the voltage across the diode is what constant, but that is not the case. We have the different models, that those are called piecewise linear models. In this question, we have to use those piecewise linear models, and if you have the idea about that, if that voltage across the diode is not constant, not fixed, then you can directly use this formula. There is some relation between I and V. I increases, V increases, or V increases means I increases. So in this way we can solve the question guys. Okay, so that question is based on piecewise linear model of the diode. Here, once the diode is in conduction, the voltage across the diode is not constant guys. And what is the cut-in voltage that is given? 0.7 volt. Like this. This is called one model. And this is 1 by RF. This is I. This is what V. Voltage across the diode. Okay. And cut-in voltage is what? 0.7 volt. Then this is called piecewise linear model. The resistance for this is fixed RR when the diode is reverse biased, that is infinite, and the resistance of this is what RF, and then this is the diode, and in that case diode can be replaced by the V gamma and RF when the diode is forward biased. V gamma is here 0.7 volt, RF is the internal resistance of that. Okay, means from this diagram you will get the idea, if the current increases, drop across the diode will also increase. What is this? This is the V1 when the current is I1. When the current increases up to I2, voltage will also increase from V to V2. This is the voltage from V1 to V2. There is a variation. So this is a very simple way to solve this question. What is the simple way to solve this question? If you have this equation V minus 0.7 upon 500 ampere, remember this is in ampere, and I is 0 for when V is less than 0.7 volt. Watch this. We have applied the 10 volt. 10 volt is greater than V, means 0.7, means definitely the diode is forward biased. When the diode is forward biased, we have to use this equation. What is the equation? I is equal to V minus 0.7 upon 500, and second equation you can get from this one. What is the I is equal to? 10 minus V upon 1 kilo ohm. This is in milliampere, remember. Or you can convert it into ampere by converting it into what? Ohm. Or you can convert it into milliampere, because we can equate it, but when both are in milliampere. From these two, V minus 0.7 upon 500 into 1000. that is in milliampere current, and second equation is 10 minus V upon 1, that is also in milliampere. Now you can equate and it will become 2 times of V minus 0.7, this is the 2 times of V minus, is equal to 10 minus V, that will become 2V minus 1.4 is equal to 10 minus V, that will become 3V, here it will become 10 plus 1.4, that is what, 11.4. What is the voltage across that? 11.4 upon 3. 11.4 upon 3, you can solve it 3 times, no? 9.3.8. 3.8 volt is the voltage across what? Diode. Means it is a very, very high as compared to what? 0.7 volt. Second thing, what is the current here? Once you have the value of V, you can find the current 10 minus 3.8, that is a 6.2 ampere, milliampere. 6.2 milliampere. This is the answer for this question. So directly one equation that is given in the question and one equation from the diagram, and directly you can solve and you will get the 6.2 milliampere. But what will be the silly mistakes? Number of students will take this 0.7. 10 minus 0.7 upon 1 kilo ohm, that answer will be 9.3 milliampere, but this answer is wrong. Some student will assume it ideal, it will act as short circuit. 10 divided by 1, answer is a 10 milliampere, ideal condition. This is also wrong, right? So that is the reason. So there may be the chance of what silly mistakes, so please take care of it. Now, any doubt up to this point? Any doubt up to this point, guys? We have number of questions on what forward bias and reverse bias junction, but up to this point, any doubt? Anyone? आप कौन कौन प्रेजेंट है भाई, बताओ जरा. हाँ, we can say Vikram. हाँ, this is a 500 ohm. This is the V minus 0.7 upon 500, because this is the current through the diode. So always remember what is the equation from this line. If that is the case, always remember this is the diode. Diode can be replaced by RF, right? And what is the total drop across the diode? V. And this is the 0.7, that is called cut-in voltage, that is the RF. So what will be the current? If the total drop across this is V, so what is the current? V minus 0.7, V minus 0.7 upon RF. And what is given here? I is equal to V minus 0.7 upon 500 ampere. Means this 500 is nothing but RF. RF is equal to 500 ohm. Why ohm? Because it is in ampere, that's why it will be in ohm. Yes. So that is the value of RF. You have given the right answer. Substitute the piecewise linear model in the circuit, then solve the circuit. Yes, you can. If you have the idea about that, then directly in the same question, you can replace the diode and you will again get the same answer. That is replaced by RF, and one you can change the position. This is the 10 volt. This is the cut-in voltage, and this is the RF. What is the RF? 500 ohm, means 0.5 kilo ohm. This is 1 kilo ohm. Directly you will get the answer. 10 minus 0.7 upon 1.5. You will get the same answer. This is called piecewise linear model. Diode is replaced by the piecewise linear model. And then the total drop from this point to this point, that is the V. Total drop from this point to this point, that is the V. Okay. So it's up to you which method you want. Then there is also a method, or directly you can use the equation. So this is on the characteristics, guys. This is on the characteristics of the diode. Now second important thing, when the diode is forward bias, this is called forward bias, then the hole will diffuse from higher concentration to lower concentration. Electron will diffuse again from higher concentration to lower concentration. There is a minority charge carrier. This is called which phenomena? When we are making the diode forward bias, remember these terms are very, very important, theoretical question, MSQ. When we are making the diode forward bias, this diagram is important. This is the minority charge carrier. This is the minority charge carrier in P side and in N side. This is the P side. This is N side. We are making it just forward bias. Right, this is the forward bias voltage. P side, N side. Now that is the initially minority charge carriers. This is called NP naught. This is called PN naught. When we are making forward bias, this is the thermally generated charge carrier initially under equilibrium condition. But when we are making it forward bias, what will happen? That hole will diffuse from this side to this side, right? Hole will diffuse from this side to this side. Here we are getting excess holes. At the same time, electron will also diffuse from this side to this side. And that is the shape. So from this shape, you can say this diode is what, this junction is what, forward bias. This junction is forward bias, right? So that is the case. Then, and now, Madhu, you are asking about which classes? Computer science engineering. Okay. So on, I will ask and I will inform you. I will share the sheet with you. This is the forward bias. Now remember, when this junction is reverse bias, अच्छा यहाँ पर बताना जो मैंने डायग्राम है अकॉर्डिंग टू विच इज द हायर कंसंट्रेशन, पी साइड और एन साइड, एन ए और एन ए, विच वन इज हायर, एन ए और एन डी. दिस इज द माइनॉरिटी चार्ज कैरियर एंड दिस इज द एन पी नॉट, दिस इज द पी एन नॉट, minority charge carrier, and we are making it reverse bias. This is the P side, this is the N side, this is the VR. Okay. Now here this is the P side, this is the N side. Then because of forward bias, excess minority carrier is injected from P side to N side. Minority, why I am saying that minority carrier injection? Minority carrier injection because what is the status of hole in the P region? This is the minority charge carrier. That's why it is called minority charge carrier injection. But when it will diffuse, it will recombine with the electron, and that's why the concentration will reduce like this. Again, the concentration will reduce like this. Here the Na is greater than Nd. Na is greater than Nd. How we can say? Because watch now, minority charge carrier is small. Here the minority charge carrier is large. So Na is greater than Nd. Second thing, when the junction is reverse bias, according to law of junction, I am going to use one important formula, guys. If you want to find the actual concentration at this point, what is the actual concentration of hole at this junction? So far away from the junction, what is the concentration? Pn naught. What is the exact concentration here? What is the P naught? Let's suppose I am giving that this is the junction. So how we can find this P naught? So that is called law of junction. So exactly at this point you can find the concentration, total concentration from this point to this point. Excess hole concentration you can find that is given by P naught is equal to Pn naught e raised to power, what is the applied voltage in forward direction upon Vt. This is called law of junction. This is called law of junction, guys. Right? Pn naught, where Pn naught is Ni square by Nd. Ni square by Vf is the voltage applied in forward direction. Vt is the volt equivalent of temperature. Pn naught is the minority. This is called law of junction. Similarly, when we are making it reverse bias, so at the junction, what is the minority charge carrier? It will become 0. So it will become 0 means we are getting this type of shape. Because 0. This dash line shows what? Under equilibrium, when there is no biasing. Just that. Again it will become 0. This is the 0. 0. So when this type of shape means we can directly say it is what? Reverse bias. This type of shape means it is, we can say it is a forward bias. In reverse bias there is a depletion capacitance. In forward bias, because of this minority carrier injection, or this is the storage of minority charge carrier hole, excess holes, positive, and that's why there is a capacitance, and that capacitance is called diffusion capacitance, because it is a diffusion phenomena. This is a diffusion capacitance. This is the concept of diffusion capacitance. Okay, that is the diffusion capacitance. Then this is the formula for the diffusion capacitance. It is an incremental capacitance defined as rate of change of injected charge, injected minority carrier charge with the voltage when the diode is forward biased. This is called diffusion or storage capacitance. That is given by dq by dv. That is called tau g. G is called incremental conductance. And what is the R? Reciprocal of G. That is called incremental resistance or dynamic resistance. G is known as I by eta Vt, or R is known as eta Vt by I. Eta Vt by I. So eta tau I by eta Vt. That is the formula for diffusion capacitance. अब आपको आ जाएगा ना diffusion capacitance. Solve question on diffusion capacitance. That will be new for you. पर फॉरवर्ड बायस में तो मेजॉरिटी कैरियर इंजेक्शन होता है ना. अमृता खन्ना, मेजॉरिटी कैरियर इंजेक्शन नहीं होता. देखो मैं बताता हूँ, दैट इज द फिनोमिना. यस, अच्छा क्वेश्चन है. देखो होता क्या है यहाँ समझना. व्हेन वी आर मेकिंग इट फॉरवर्ड बायस, ओके एवरीवन टेल मी, हियर इट इज होल. सर्जिकल स्ट्राइक तो सुना ही हो ना. हियर इट इज अ होल, हियर इट इज अ मेजॉरिटी. यस, majority, large number of holes. Here we are having a very few number of holes because it is n type, or there are large number of electrons are here. These are the electrons and few holes. Okay, when we are making it forward bias, hole will inject from this concentration to this. Hole will move from this side to this point with the help of diffusion. Because when we are making it forward bias, barrier will reduce and hole will move from this side to this side. What is the status of hole in this region? It is the majority or minority? What is the status of hole in P region? Minority. And that's why this phenomena is called minority carrier injection, because hole will inject from P side to N side. This phenomena is called minority carrier injection. Carrier injection, and that is called minority charge carrier storage also. Now it is clear? Yes, Shivani, you have given the right answer. Nitish, very good evening. So this is the minority. Similarly, when the electron move from this side to this side, here it is a majority, but once it is enter into the P side, it is a minority charge. So this is called minority charge carrier injection. Further recombination, and finally reach to what? Concentration will reach to what? Thermally generated charge carrier. Okay, now it is clear why it is called minority charge carrier injection. That was the question in gate exam. That was the question in gate exam. Now remember this, when this type of diagram is given, that junction is forward biased. Here we are having the excess hole concentration. Watch this. It is called excess hole is stored here. This is called minority charge carrier storage. But here what will happen? Initially the concentration of hole was high, but now the concentration of hole reduces. So that is the deficiency of hole. This is negative. This is the deficiency of hole in this region. So when it is forward bias, excess minority charge carrier storage. When it is reverse bias, deficiency of minority charge carrier here. So that is called charge control description. Charge control description. Diffusion तो majority carrier का ही हो रहा है, from higher concentration to lower. But injection किसका हो रहा है? When we are injecting, so that is called what? Minority carrier. Okay. Then I think both the diagrams are clear. Forward bias and reverse bias. Forward bias. This is called reverse bias. Okay. Now, because of these capacitance CD and CT, because of this minority carrier storage, there is another concept that is called switching time. Switching time. This is another very important concept. Because of this minority carrier storage, when we want to switch from forward bias to reverse bias, diode from forward bias to reverse bias, this is called reverse recovery time. It will take time. Or from reverse bias to forward bias, this is called forward recovery time. Forward recovery time, guys. So tell me, guys, which one is higher? Reverse recovery time or forward recovery time? Everyone, tell me, which one is higher? Forward recovery time or reverse recovery time? Reverse recovery time is more than the forward recovery time, guys. Reverse recovery time is more, very high, because when we are moving from forward bias to reverse bias, first of all we have to remove this minority charge carrier, and then depletion layer will increase, because again there is a deficiency of minority charge carrier. So that is what, there are two types. One is called storage time, during which this excess minority charge carrier is removed, and after that depletion layer will increase. That is called transition time. So there are two times, one is called transition time, one is called storage time. So what is the reverse recovery time? Transition time or storage time. So during transition time, diode almost act as what? Short circuit. No doubt it is reverse bias, but during transition time it will almost act as short circuit. So if there is any diagram, for example, I am giving you one question. This is a 10 volt, it is given, 1 kilo ohm it is given. It is just, we have make it what? Reverse bias. It is under storage time. Tell me what will be the current? Tell me, guys, what will be the current I in this diagram? It is under just during what? Storage time. I am just asking what is the value of the current during storage time, less than Ts. Just I have make it what? Reverse bias. what will be the current. Now, during storage time, diode will act as what? Short circuit. Diode will act as short circuit. Now, this is the short circuit. This is the 10, this is the 1 kilo ohm. What will be the current? Current will be in this direction. 10 divided by 1, 10 milliampere. But I have given the direction here. So this is a what? Minus 10 milliampere. Are you getting my point, Chinmay? Or Google Trends? So Google Trends, this is the minus 10 milliampere. Current will move in opposite direction actually, because it is reverse bias, and it will act as almost short circuit during storage time. So remember, please take care of sign. Okay. So that is a very important question here. Now, there is a one extra thing that is given, because you are asking us, sir, they are asking some extraordinary questions sometimes in that. So Amrita, how you are getting the point 1 milliampere? 10 divided by 1 kilo ohm, that is kilo ohm. So current will be in milliampere. Now, when we are dealing with the diffusion capacitance, so actually what we are doing, we are connecting the DC. We are connecting DC supply here. This is forward bias by DC voltage, 5 volt, 10 volt and so on. So we are having the constant current. When we are having the constant current, so what is the formula for series? Tau G, tau I by eta Vt. Right, but if we are giving the what? AC supply for low frequencies. For low frequency, the formula will become 1 by 2 tau G. 1 by 2. Or if the frequency is very high, for example, there are two types of sinusoidal signal. It is of low frequency, it is of very high frequency. So this is a signal. Then for high frequency, diffusion capacitance will become tau upon 2 omega. More will be the frequency, less will be the diffusion capacitance. It is inversely proportional to frequency. Tau upon 2 omega raised to power half into G. This is important formula. Okay. But sometimes they will give new question, or they will ask what? They will ask what is the effect of the frequency. If we are increasing the frequency of the signal, diffusion capacitance will reduce. Diffusion capacitance will reduce, guys. More will be the frequency, less will be the diffusion capacitance. Remember, that is the formula. Okay. Otherwise, for DC, it is independent of the frequency. Tau I by eta Vt, tau G. Okay, then next. कोई बात नहीं, कैलकुलेशन मिस्टेक तो आप हटा सकते हो. जैसे ये क्वेश्चन आया था, that was the question in GATE exam. In the circuit shown below, the switch was connected to the position 1 at t equal to less than 0. At t equal to 0, it is changed to position 2. Assume that the diode has a 0 voltage drop and a storage time Ts. For that, VR is given by. अब तो सॉल्व कर लो कि what is the value of the VR? Minus 5 volt, plus 5 volt, between 5, then so on. But always check the polarity. This is plus, that is minus. Initially it is connected to 5 volt. Exactly at t equal to 0, the situation is switched from 1 to what? 2. And during the storage time, what is the VR? So it will act as what? Short circuit. During storage time, it will act as short circuit. So what is the VR? Minus 5 volt. VR is minus 5 volt. And current will move in opposite direction. Current will move in opposite. That's why we are getting the VR negative. VR negative. Same type of question. Okay. Or one question we will solve. The small signal capacitance of an abrupt P positive N junction is 1 nanofarad per centimeter square at 0 bias. If the built-in voltage is 1 volt, the capacitance and reverse bias voltage of 99 volt is. So reverse bias means, already I have said, built-in voltage is given P positive N junction means what? P side, the Na is very greater than Nd. And W is nearly equal to what? Wn. and only the capacitance is asked. Already I have given, you can directly use this formula. CT2 upon CT1 is equal to root over V0 plus VR1, V0 plus VR2. So what is the VR1? Zero bias, means VR1 is 0. Or what is the built-in potential? 1 volt. 1 plus 0 upon 1 plus 99. CT2 will become CT1 upon 10. Upon 10. What is the CT1? 1 nanofarad upon 10. What will be the answer? 0.1. When the reverse bias voltage will increase, what about the capacitance? Capacitance will decrease. Capacitance will decrease, guys. So that is the question. That is the question. Okay. ऐसा आप कर सकते, बना सकते हो. ये है केस. Is it audible ना? तो आप तो मेरे ख्याल से आप ट्रांजिशन कैपेसिटेंस में आपको कोई प्रॉब्लम नहीं है ना. 0.1 nanofarad, that is the answer. 0.1 nanofarad, that is the answer, guys. Okay, तो number of questions, straightforward questions we are getting. Okay, बहुत सारे ऐसे क्वेश्चंस हैं. हाँ, ये थोड़ा सा जैसे अच्छा क्वेश्चंस आया था एक बार, इसकी थोड़ा सा प्रैक्टिस कर लो. देखो ये वाला जो डेरिवेशन है ना, इसको आप जरूर प्रैक्टिस कर लीजिए. द इलेक्ट्रिक फील्ड प्रोफाइल इन द डिप्लेशन रीजन ऑफ पी एन रीजन इन इक्विलिब्रियम जोन, विच वन ऑफ द फॉलोइंग स्टेटमेंट इज नॉट ट्रू, इज नॉट ट्रू. तो दैट इज द इम्पॉर्टेंट वन. तो इसमें थोड़ा सा मैं आपको बता दूं, जैसे दो हैं डायग्राम. नॉर्मली ड्यूरिंग डेरिवेशन व्हाट वी आर डूइंग, दिस इज द पी टाइप एन टाइप. quick revision. That is the case. Normally what we are doing, the p side doping is very high left and n side the doping is very less. So this is p type, this is n type. That is reverse bias. Then p side the doping is very high. So here we are having the negative acceptor ion. This is the concentration of acceptor, negative side. Depletion rate is very less, and this is the concentration of on donor side. Or when we are using, this is the zero level, this is the concentration negative ion, this is the positive ions, and we are using the Poisson's equations here. Minus rho by epsilon s. Here rho we will use Q and D. Q and D. Why? Because Na is very high as compared to that. Now we are having, or we are using that formula already have given, Na into Wp is equal to Nd into Wn. Here the depletion width is given by Wp, this is the 0. Here the depletion width is given by Wn, x. When I am integrating it, this equation, we will get electric field like this. What is the integration of the rectangular shape? Triangular. So this type of shape. So from this we can say there is a uniform doping in p side. There is a uniform doping on the p side. Because of the uniform doping we are getting this type of shape. Or uniform doping on the n side. Because of this uniform doping we are getting this type of shape. And now it is a triangular. And what is the integration of that? We are getting this type of potential junction. This is the increases and that is the case. And this is called Vj. Exactly at Wn, this is called Vj. V0 plus Vr. And now here exactly at Wp it is 0. This is called boundary condition. Or exactly at junction, this is the junction, Pn junction, P positive N junction. We are getting maximum electric field. This is the electric field. Right, maximum electric field. And here we are getting the, when we are integrating, we are getting the potential. So this diagram is very important. But watch it carefully. That is the opposite. It is given opposite. Just reverse of that. Means it is not a PN. It is a NP junction. It is what? N positive P junction. Because this is the diagram for what? P positive N junction. So what is the diagram for N positive P junction? N positive P junction just opposite. Now we are having quickly, can you draw? Same thing, but this time that will be the case. Now here it is a positive ion, here it is a negative, and when I am integrating it, we are getting this type of electric field, and exactly at junction it is maximum. So this is the N, this is the P, this is the N positive P junction. Left hand side it is N, right hand side it is P. This is the negative positive ions. Okay, finished. Now, okay then. So you can vary, and this is uniform doping. It is a uniform on the N side, it is uniform on the P side. Because of this uniform doping, we are getting the rectangular shape here. Right, and that is a straight integration of rectangular is triangular. So this is we are getting. Now uniform doping. So what is given here? The left side of the P junction is N type and the right side is the P type, correct? Both N type and P type depletion region are uniformly doped, correct? Right. Now this is the 0.1 minus 0.1, no? Because it is less, na? Less, it is minus 0.11. So means we can say on N side the doping is very, very high. Now last statement, if the P type region has a doping concentration of 10 to the power 15, then the doping concentration in the N type region will be 10 to the power 16. You can verify it. How? Na into Wp is equal to what? Nd into Wn. So what is the Wn? 0.1. 0.1. This is 0.1 only. What is this 1? Minus means it is the width is 0.1. This is 1. Here it is 1. Or Na is given as 10 to the power 15. So what will be the Nd? 10 to the power 16. That is also correct. So which answer is wrong? C. And how you can verify C is the wrong? Because what is the potential difference? Potential difference is the integration of the electric field. Or what is the integration? Integration means area of the curve. So what is the area of the curve? Half of base. Base is 1.1 into height. What is the height? 10 to the power 4. And remember that is in what? Micrometer. Or this is in volt per centimeter. Can you convert it into micrometer? Can be converted into what? Centimeter, 10 to the power minus 4. You will get 1.1 divided by 2 volt, or you can convert it into what? Millivolt. So you are not going to get this answer, 700 millivolt. That is wrong. You are getting the 550 millivolt as a potential difference. So that's why the C is wrong. Both are correct. You have to find the integration of that curve. Take care of units only. That is also correct. So that derivation is important in PN junction. This is all about what? PN junction, guys. So already I have given the law of junction, diffusion capacitance, transition capacitance, and so on. We have solved number of topics here. Try to solve these questions, previous year questions, number of previous year questions we have. Right. Now guys, this is time to start. One thing is also spatial diodes. One is what? Spatial diode is what? Varactor diode. Varactor diode means because we have deal with what? Transition capacitance. So on this capacitance, varactor diode is best. What is the varactor diode? This is the symbol for the varactor diode, variable capacitor. And already I have given CT is proportional to what? Vj raised to power minus 1 by 2 for step graded junction. Vj raised to power minus 1 by 3 for linearly graded junction. Linearly graded junction. That is for step graded junction. remember. By changing the value of the voltage, we can change what value of the capacitor, and that is called what? Varactor diode or volta cap or voltage variable capacitor. So these are the name, right? These are the name here. So any doubt? Okay. So that is the model. Remember, they can ask one question on model, guys. First of all, that is the value of the capacitance. This is the parallel resistance. Because it is reverse bias, so what is the resistance of the diode? Very, very high, right? So this is the diode. So we are connecting the two. This is very, very high resistance, and that is the transition capacitance, very low. Okay. Now we are connecting this lead, and this lead has some resistance. So this is represented by this one. Very small resistance because of the lead, that is the RS, packing resistance this is called. So what is the value of RS? Only 8.5 ohm. What is the value of the capacitance? That is in the range of picofarad. And what is the resistance? It is range of 1 mega ohm. So normally we can remove it, right? But it is in picofarad. So this is the model. So we can expect one question on what transition capacitance, where we have to convert this capacitance by using this model, and we have to solve questions by applying the concept of network. And the concept of network, first order transient concept, how the capacitor will introduce the delay in the circuit and so on. Okay, that is called varactor diode. It is used for what? Frequency tuning, voltage tuning. In parametric amplifier we are using the varactor diode. जहाँ भी हमको जरूरत है ना वेरिएबल कैपेसिटर के लिए, फ्रीक्वेंसी को ट्यून करने के लिए, we are using the varactor diode here. Hope up to this point PN junction is clear. Now guys, BJT bipolar junction transistor. Okay, tell me here, थोड़ा सा जरा आप लोग पूरे जोश में हो. How is the जोश? अभी तक तो हो गया रिवीजन, एंजॉय कर रहे हो आप लोग. सेमीकंडक्टर फिजिक्स इज क्लियर. हाँ, यू आर यूजिंग दैट इन व्हाट? क्लैप ऑसिलेटर, कॉलपिट ऑसिलेटर, वेरिएबल कैपेसिटर. नो, इन कॉलपिट नहीं, हार्टले ऑसिलेटर. In Hartley oscillator we are having the variable capacitor. In clap oscillator we are having the variable capacitor. Yes, you are correct. In Colpit oscillator we are having the variable inductor. In Colpit oscillator we are having the variable inductor, guys. तो देखो इतने, these all are the important points. That is one thing I have given, just what charge control description of the diode. Charge control description of the diode. चलिए आप देखते हैं नेक्स्ट बीजेटी, क्विक रिवीजन ऑफ बीजेटी. On biasing and stabilization we have to solve some questions from analog, guys, but here you will get the basic idea about the internal structure of what BJT and about the characteristics. Now BJT, what's the shape? Emitter region, collector, base. Base is the thinnest part. Emitter has the highest doping, collector is the largest one, area is the highest, because it acts as source, it acts as sink, and the base will provide the electrical isolation between emitter and what? Collector, and it will also provide a terminal where we can apply a voltage, that is called controlling voltage, and indirectly we are going to control the current here. We are going to control the current here. Okay, so that is the shape. So we are having the two junctions, one is called emitter junction, one is called collector junction. Okay, emitter junction and collector junction, that is the symbol for NPN transistor. because in NPN transistor current will enter through the base, through the collector, and emitter current is outside. So IC plus IB is equal to I, that is called Kirchhoff's current law. IB plus IC is equal to I. In case of PNP transistor, current, emitter current will enter, collector current will leave the transistor, base current will leave the transistor. Again I is equal to IC plus IB. That is the equation, guys. Now, so doping of the emitter is highest and area of the collector is highest, and that's why it is a asymmetrical device. Asymmetrical means no doubt it is a PNP or NPN. When we are watching a PNP or NPN, so what we can say that we can use this N or that N as a collector? No. It is the asymmetrical device, means we can't use emitter as a collector or collector as a emitter, right? So we have to choose that emitter, and that's why we are having the different modes of operation. What are the different modes of operation? Cutoff, active, saturation, and reverse active. Active mode is also called normal active mode or forward active mode. This reverse active mode is also called inverse active mode. Cutoff means both junction reverse bias, very high internal resistance. What is the use of the cutoff? Just for a switching action, off switch we are using. Then what active mode, and active mode is used for what? Excellent transistor action, for amplification of the signal. Transistor action means, what is the meaning of the transistor action? Transistor, transfer register. Transistor is what mixing of the two words, that is the transfer plus register, transistor. So transfer of current from low resistance to what? High resistance. That is what transistor. Low resistance to high resistance. So that is the transistor action, the amplifier. Saturation again for switching, very low internal resistance. Reverse active means what? Emitter junction is reverse bias, collector junction is forward bias. Very poor transistor action, but we are using in some cases, rarely used for low amplification. When low amplification is required, we are using it. Right, sir, for BJT using as a switch, it is using between the cutoff and saturation. That is, yes, these are the two extreme ends of the characteristics, guys. Extreme ends of the character. So there are four modes only. Now, when we are talking about the current components, watch this. This diagram is important. For example, it is a PNP transistor. Emitter junction is forward bias, collector junction is reverse bias. When it is forward bias, again the hole will diffuse. Watch this, that is the question. When we are making PNP transistor, emitter junction is forward bias. The forward bias will reduce this barrier. Hole will move from this point to this point, from P region to N region. Tell me, it is, what is this? Majority carrier injection or minority carrier injection? Majority or minority? We are just reducing the barrier. Hole will move from P side to N side, and it will recombine with the electron. Because of that recombination, base current will produce, and the remaining hole will reach to collector, and they will constitute a collector current. They will constitute a collector current. So when the hole will move from P side to N side, so in a emitter it is a majority carrier, in base it is a minority carrier, and that process is called minority carrier injection. Then recombination, it is a, yes, minority carrier injection, and then there is a recombination, and finally they will reach to what? Collector. They are collected there, and they will constitute a current, collector current. Now there is also one current, because that junction is reverse bias, there is a current that is called ICO, reverse saturation current. ICO, that will move from N side to P side, and because of that, normally we are giving like this arrow, IC is equal to alpha I plus ICO. So this is the formula valid for what? Active region. So IC outside, IB outside, I inside, and we are having the two current. ICO has the two component, because when any junction is reverse bias, like this junction is reverse bias, it has the current. So already I have given the formula for the current. What is the reverse saturation current? AQ dP Pn naught upon LP. AQ dN NP naught upon Ln. So that is the reverse saturation current because of the holes, and that is the reverse saturation current because of the electron, and that is the total reverse saturation current when collector junction is reverse bias, ICO. O for reverse saturation current, C for when the collector junction is reverse bias. We are also having the IEO. What is the IEO? When the emitter junction is reverse bias. Okay, tell me which one is higher normally, IEO or ICO? Which one is higher, IEO or ICO? IEO is the reverse saturation for current for emitter junction when the emitter junction is reverse bias. ICO is the reverse saturation when the collector junction is reverse bias. So doping, IEO is higher or ICO? IEO, Vikram. Achha, tell me, doping of emitter is very very high as compared to collector. Try to understand. When the doping of emitter is high, so what about the minority charge carrier in emitter region? According to mass action law, it is less. Or what is the minority charge carrier in collector region? It is high, right? Or reverse saturation current depends upon what? Minority charge carrier. This is the minority charge carriers. That's why this term is high. A base region is same for both, and when this is high, current will be high, and that's why IEO is less than what? ICO. IEO is normally less than ICO. Reason simple, NE is greater than NC. So because of higher concentration, minority charge carrier concentration will reduce, and reverse saturation current directly depends upon the minority charge carrier. तो sometimes क्या होता है, IEO, तो ये आपको याद रखना है. हाँ, if both are equal, NE or NC are equal, then both will be equal. NE or NC. NE means doping of the emitter, NC means doping of the collector, NB means doping of what? Base. Doping of base. Okay then. I think this is clear to you. Now, second one, when sometimes they will give this diagram, for example, emitter junction is forward bias. So forward bias, to watch this, this is the potential barrier, it will reduce by what? VEB. It will reduce by the forward bias voltage. So what is the new potential barrier? V0 minus VEB. Or when we are making the collector junction reverse bias, it will increase by what? VCB. So what is the total potential barrier? V0 plus VCB. Here it will become V0 minus VEB. Now watch this. Already I have given a charge control description of the diode. So here this junction is forward bias, and that's why excess minority carrier will injected here. Here. Because the doping of emitter is very very high as compared to base, you are getting this type of diagram. Right? After that, this junction is reverse bias. When this junction is reverse bias, what is this? 0. That is the 0. So in first part of this session already I have given this diagram. Where is that diagram? 1 minute. Chart. This is called charge control description of the diode, guys. Charge control description of the diode. This is a very very important one. This was the diagram. Watch this. This was the diagram, charge control description. That is the forward bias and that is the reverse bias. Now mix. No, that is the diagram. For transistor, there are two junctions. This junction is forward bias, that junction is reverse bias. From watching this diagram, we can say it is in active region. That was the 2-mark question in GATE exam. This is forward bias, that is reverse bias, and that transistor is in what? Active region. And that was already I have explained. Forward bias and reverse bias according to law of junction. According to law of junction, guys. Okay. Now The law of junction, if this question is asked, already I have given what is the concentration of this when it is forward bias, that is the case, or when it is reverse bias, negative. Because of this negative, it is almost become 0. This will become almost 0. This is the forward bias. P naught is greater than P n naught. P naught means 0. It is very less as compared to P n naught, or nearly equal to 0. Here this is very large because of forward bias. Okay. Law of junction. So there was one question in law of junction, guys. Now, when we are making a forward bias, because it is a class of EDC, electronic devices and circuit, then this junction is forward bias, this junction is reverse bias. So when suppose it is a NPN transistor, what will happen? When this junction is forward bias, the electron will move from this side to this side, hole will move from this side to this side. Now there are two currents, one because of electron, one because of holes. One because of electron and one because of holes. But that collector current is constituted only by what? Electron. Why? Because electron will move, some electron will recombine in the base region and remaining will reach to what? Collector region, and they will constitute collector current. Okay. Then, but emitter current has two components, one because of the electron, one because of the hole. So out of this is useful. Out of this is useful. At the same time, in this junction, there will be some recombination. That recombination will also constitute a recombinational current, and that is also the part of what? Emitter current, but that is not useful for what? Collector current. Okay. So that is the problem. So when we are considering all these parameters, then we are getting a very important formula, because there is a when the electron will move, hole will move from right side to left side, electron will from left side to right side, only the electron is useful. Second, there is a recombination, that is also not useful. Third thing, some electron will recombine in the base region, and that's why it is not the part of what? Collector current. So what is the efficiency here? What is the alpha factor here? So that is the important formula here, alpha. A small signal or sinusoidal common base current gain is defined as, common base current gain alpha is defined as, this is the first term, this is the second term, and that is the third term, guys. One by one I am going to explain this. Then this is the first term, right? This is called base. 1 minute, there is a, okay, this one is the written. Please change here. This is the emitter injection efficiency. This is the emitter injection, and that is the base transport factor. Base transport factor. And this is the emitter injection efficiency. Injection efficiency. JNE upon JNE plus JP. This is the current density because of the electron. This is the electron plus holes. So only out of electron plus hole, electron is useful. Then there are three currents. One is what? Because of the electron. One is what? Because of the holes. One is called recombination current in the junction of what? Emitter and base. But out of these three, electron and hole is useful, and out of hole and electron, only electron is useful, and out of any, some will recombine in the base region and remaining will reach to collector, and that will reach to the collector. That is important. So JNC. So when we are considering all these three, we have to multiply. So directly you can recall this formula. Okay, sir, JNC plus JNE is useful from three terms. Where is the recombination current? Out of the JNC and JNE, right? Okay, 1 minute. This is the JPE. One because of hole, one because of electron. Now out of the JP and JNE, only JNE Now second term. Then out of the JNE, only that is useful which reach toward collector. That is the case. This is called alpha transport. This is the transport factor. This is called what? Emitter injection efficiency, and that is called recombination factor. First one. This is the recombination factor del. So this is a multiplication of del dot gamma dot T. They will ask. It is an important question on what? Emitter injection efficiency. Now it is clear to you? यहां तक सब कुछ क्लियर हुआ? Can we potentially ask, sir, in exam means what is the ask? They will give you the data and then you have to find the value. No doubt up to this point? Okay, then next one. So that is important. Now, second important point is what? Early effect or base width modulation. Early effect or base width modulation, guys. Early effect or base width modulation means simply this is the transistor, that this is the base region, just I am zooming it. Now in this region, if it is a PNP transistor, we are making this junction reverse bias. Okay, what will happen when we are making this junction forward bias? Hole will diffuse, they will recombine with the electron, and the remaining hole will reach toward collector, and they will constitute a collector current. That is the simple phenomena. But when we are, this is the physical width WB, we are having a large number of electrons from this point to this point. That's why when the hole will enter, they will recombine with the electrons. For example, 1000 hole will enter, out of 1000, 100 will recombine, remaining will reach toward P, and they will constitute a collector current. But when we are making it reverse bias, then because of the reverse bias, depletion width will increase. Now the depletion width will increase up to this point. Depletion width means only there is an immobile charge carrier. There is no electron in this region. So this is called depletion width. It will increases in the base region. Now this is called effective base width. Effective means there is large number of electrons. When the hole will enter, only in this region recombination will occur, and in this region there is no recombination. So because of that, when the 1000 the hole will enter, only 50 will recombine and 950 will reach here. Initially 100 out of 1000, 100 recombine, 900 reach here. Now the 950 will reach there. When the 950 will reach there, Then what about the collector current? Collector current increases. Alpha increases. Transport factor alpha what increases? Collector current increases because of the early effect. And what about the effective base width? Decreases where the recombination will occur. That is called base width modulation. And when the recombination decreases, base current will also decrease, because base current is the recombinational current. Less will be the recombination, less will be the base current. So that is called what? Early effect or base width modulation. Finally, when we are applying the more and more reverse bias, complete base region is converted into depletion region. When the complete base region is converted into depletion region, so WB will become WD. So what is the effective base width? 0. Because effective base width is the physical base width minus what? Depletion width. Effective means where the recombination will occur. So when it will become 0, what will happen? Transistor action ceases. This is called punch through or reach through. Punch through or reach through. Transistor action ceases. Or here one important point, because of this base width modulation or early effect, emitter current also increases. Emitter current also increases because it is a diffusion current. Concentration gradient increases, that's why the emitter current will also increase. Concentration gradient will increase, IE will increase because it is diffusion current. So that is the early effect. Why it is called early effect? Why it is called early effect? Everyone give me the comments in comments box why it is called early effect. So this is the base width modulation. So normally we are getting question on early effect or base width modulation. So this is nothing but variation of the effective base width where the recombination occur with VCB is called base width modulation or early effect. Right? So that is the reason. Already I have given what are the consequences of the early effect. Okay. Then straightforward questions we are getting from the early effect. This was the question. Why it is called early effect? Yes, discovered by JM Early. That's why it is called early effect. अब बताओ यहाँ. That is the based on what charge control description of the diode. Which answer is correct? Which answer is correct? बताओ भाई क्या होगा आंसर. Option C. Ashish Kumar, how are you? Very good evening. Rupesh Reddy. Yes, inverse active mode. Now, in this case, according to charge control of description, you are watching negative value, sir. What is the meaning of this negative? Already I have said, na, deficiency of law of junction means what? Deficiency of minority charge carrier. That's what is negative. Or here it is what positive value means what? Excess minority charge carrier. It is increases. So just we are comparing with what? This is the, with this level, 0 level. This is called negative means deficiency, or positive means excess minority charge carrier, means this junction is forward bias, that junction is reverse bias. If the emitter junction is reverse bias, collector junction is forward bias, means what? This is a inverse active mode. It is a inverse active mode. See. Okay. So this is the normalized excess carrier concentration. So excess means what? Positive. If it is negative is given, means what? There is a deficiency. When this is the junction is reverse bias, according to law of junction, there is a deficiency of minority charge carrier here. Okay. So ये हो गया. That is the x and y axis are not to the scale. Just to take care of that and you will get the idea. Okay then. This type of questions in BJT from EDC. Then this is a good question. Watch this. In 2016, 2 marks. The injected excess electron concentration profile in the base region of an NPN BJT biased in the active region is linear as shown in the figure. If the area of the emitter base junction is 0.001, mu n is 800 centimeter square per volt second in the base region and depletion layer width are negligible, then the collector current at room temperature is given by. So देखो, this junction is forward bias, this junction is reverse bias, that's why that concentration will become 0. This is the excess concentration of electron 10 to the power 14, and what is the concentration? 0. Now this width is also given, and that is what diffusion phenomena. The electron is moving from higher concentration towards lower concentration in this case. Now in this is the right direction. First of all, watch the direction. In case of NPN transistor, emitter current is outside, collector current is inside, base current is inside. Yes, collector current is inside, base current is inside, emitter current is outside. Means this is the right direction. Means what will be the answer? Answer will be positive. One thing, answer will be positive. Why answer will be positive in this case? Because that is the correct direction. IC inside, IB inside, IE, or IC is asked. The injected excess electron concentration profile in the base region of this inactive region is linear. If the area of the emitter base junction is area is also given, mu n is given, depletion layer width are negligible, then the collector current it is asked. Collector current. So it is a diffusion current. How we can solve? So diffusion current, because of the electron, it is given by IN AJN AQ DN dP by dx. dN by dx. This is called concentration gradient. Now according to Einstein equation, dN by mu n is equal to Vt. What is the dN is equal to? Mu n Vt. Mu n is given in the question, Vt is given in the question. Mu n is given, area is also given, and Vt is given. Mu n into Vt, it will give you the dN. Q is also given 1.6 into 10 to the power minus 19. Now you can find this and this. Now what is the concentration gradient? What is the slope of this line? Slope of this line. So what is the concentration at this point? 10 to the power 14. What is the concentration? 0. What is this? 0.5 micrometer. The slope of this line is given by N2 minus N1 upon X2 minus X1. What is the N2? 0 minus 10 to the power 14 upon X2 minus X1. X2 minus X1, 0.5 micrometer. Minus 4 centimeter it will become. It will become 18 with negative sign. So when I am putting the negative here, you will get the negative answer, IN. What is the meaning of the negative? this current is what in negative x direction. So when we are writing the formula, actually this is the current in this direction, in positive x direction, and that's why this is the formula. We are getting the negative value, means actually the current is in this direction. And what is the IC? IC is also in this direction, so we are getting the IC positive value. This is the negative value, but actually the current is moving. When the electron is moving from this side to this side, current will move in opposite direction, or IC is also in the same direction. That's why finally you will get the positive answer. Finally you will get the positive answer, because IC is minus IN. Minus minus it will become plus. Put this value. A is given, Q is given, Dn is given, Dn by dx is 2 into 10 to the power 18. Right? So this is the value. So is it clear, guys, how to solve the question on diffusion? That is a good question in transistor. We are getting this type of questions. Okay then. Look, biasing and stabilization means transistor in active region or saturation region, or what cutoff region, how we can verify what is the self biasing, what is the fixed biasing, collector based bias circuit. That is the part of what analog. That is the part of analog. In EDC, we are getting this type of question. What is the diffusion phenomena, drift phenomena, what will be the current? Okay, so that is important. So early effect we are using in what EDC as well as what in analog. But analog we are dealing with all type of biasing and stabilization of what BJT. Please watch my previous session on that. Up to this point, any doubt? Okay, now next topic. Just I will give you the basic idea about the common emitter, common collector and common base characteristics. And after that we will start what MOSFET and MOS capacitors, guys. Okay then. Now next I am going to start. अब आते हैं ज़रा, ये तो क्वेश्चन हो गया सॉल्व, अब आपको क्लियर भी हो गया. वी आर गेटिंग दिस टाइप ऑफ क्वेश्चन गाइस. देन देखो, when I am talking about the characteristics, please revise the characteristics for common base, common collector and common emitter. As you know, there are mainly three configuration: common base, common emitter and what? Common collector. Which one is most popularly used configuration? Tell me. Which one is the most popularly used configuration? Common emitter. Right. Now, this is the common base. Here, we are giving input to emitter, output from the collector, base is common. And here, most important thing, input current is emitter current, output current is collector current, input voltage is VEB and output voltage is VCB. So there are always two characteristics. One is called input characteristics, one is called output characteristics. Input characteristics means the input voltage is the function of output voltage and input current, right? And output characteristics means output current is the function of the output voltage and input current. That is, for example, IC is equal to alpha I. IC is the output current, alpha I is the input current. So this is called IC is the function of IE, as well as there is a early effect also. Because of early effect, it is also the function of VCB. So in case of common collector, common base, we are getting this type of characteristics. Common base, we are getting this type of characteristic. This is the IC, this is VCB, and that is what? Different values of IE. Different values of IE. So we are getting a constant current characteristics. This is a constant. When it is in active region, we are getting almost constant current. So this region is called active region, this is called cutoff region, and that is called what? Saturation region, guys. So when we are talking about the constant characteristics, means IC is solely depends upon what? I, and it is almost independent of voltage VCB. That's why it is called current controlled current source. That's why it is called current controlled current source, common base. That is important question in EDC. Which one is the current controlled current source? Then it is what we can say, it is a common base configuration. Constant current characteristics. Effect of early effect is negligible. And then what are the properties of that? Lowest input resistance, highest output resistance, lowest AI, highest AV, highest voltage gain. It is in the case of common base. Highest voltage gain, but current gain is only alpha. Alpha is less than 1. 0.9 to what? 0.998. 995 only. So this is the value of alpha. Lowest current gain, highest voltage gain, moderate power gain, phase shift is 0. Common base amplifier will offer largest bandwidth and it is more suitable for high frequency application. High frequency application. These are the properties of what? Common base. Then what are the applications of the common base? In MSQ you can get this answer as a constant current source, already I have given. Because the phase shift is 0, voltage gain is very high, that is called non-inverting, because phase shift is 0, voltage amplifier. As a high frequency amplifier, current gain bandwidth product is constant, gain is low, bandwidth is very high. As an impedance matching device between low resistance to high resistance, its input resistance is very low and output resistance is very high. Very high, and that's why it is used for impedance matching device. We can say it is used as a buffer. Yes, it is. This is the use of that as an impedance matching device between low resistance to high resistance. That is called what? Buffer. Buffer means what? Simple. Watch this. For example, if suppose you want to connect a current source here, this is RL. For example, it is 10 kilo ohm. Its internal resistance is also 10 kilo ohm. And this is the 5 ampere current. So tell me, what will be the current through the RL? the current through the RL will become what? 5 by 2, half, just a half, because it's RS and RL are same, it will become half. Now I want to transfer the complete current, then what I can do? I can connect a buffer here. That is called impedance matching device. Now this is the RS, 10 kilo ohm, it will remain same. This is the 5 ampere, it will remain same. This is the RL, it will remain same. $10 kilo ohm. Then what is the buffer here? Its output resistance is very high. This is the output resistance of the buffer, that is in the range of what? Mega ohm. And its input resistance is very low, right? Very low as compared to RS. It is in the range of ohm. And what is the current gain? Alpha. Alpha is nearly equal to 1. What will happen when it is a very low? The complete current will enter into the common base configuration. Complete current will enter into the common base configuration. Now what is the current gain? 1. That's why you are getting the 5 ampere. Now complete current will pass through the RL because its output resistance is very high. So that is called transfer of the current. That is called what? Transfer of the current, guys. So this is the case. Okay. That is the case. So buffer means impedance matching device. Impedance matching device. Now, what will happen, guys? Try to understand why we are having the high value of the resistance. Why we are having the high value of resistance? Load resistance. We are having the high value of the load resistance because when we are connecting a number of load in series. Number of load in series. For example, in Deepavali, we want to design what? That lights. So what we are doing? We are connecting the number of bulbs in series. When we are connecting the number of bulbs in series, means actually we are connecting the resistance, number of resistance in series. That's why the overall value of the resistance will increase. Now it wants more voltage because when the resistance increases, definitely current will reduce. So we have to maintain the same current, we have to maintain the same voltage across each resistor. So we want a device which can maintain the same current or which can give the very high voltage gain. So which that device is what? That device is common base. That device is common base, guys. So that is the common base configuration. Now please, was any doubt then, everyone? Any doubt in this case? हो गया Vikram? Now it is clear why it is called buffer. Because its current gain is what? 1. Because its current gain is 1, it will not amplify. So buffer or inverter, there are two things. So current gain is 1, but voltage gain is very high, or it is also called impedance matching device. So what is the impedance matching here? Here the low resistance is required so that it can transfer the complete current. Here the high output resistance is required so that output current is transferred to RL. So it is a matching low to high resistance, and that is called buffer. Current buffer, because its gain is 1. Now it is clear. Now, most popularly used configuration is common emitter. This is the common emitter, and input resistance low, moderate, output resistance moderate, current gain moderate, voltage gain moderate, but the power gain is highest in case of what? Common emitter, and it is used in multi-stage amplifier. In between we are using the common emitter configuration, that is the multi-stage amplifier. Its power gain is highest among the 3 configuration, right? And we are getting the characteristics like this: somewhat elevated curve, right? This region is called saturation region, this region is called active region, that is called cutoff region. Or in active region, that is the curve is what? Elevated curve. Why? Because of which effect it is elevated. That is the output characteristic of common emitter. In case of common base, that is a constant current characteristic, like this. But here it is elevated. Because of which effect it is elevated? Tell me. Now, in case of common base, this is the IC, this is the VCB, and that is the function of what? IB. But in case of common collector, common emitter, it is the function of what? IB. So IC is equal to beta IB. That is the formula. IC is equal to what? Beta IB, and it is elevated because of early effect. Yes, that is the right answer, Nitish, Ashish, Vikram. Because of early effect. Because the effect of early on alpha is negligible, but on the beta is very, very large, and that's why it is elevated curve here. So that is in active region. When the transistor is in active region, it behaves like an what? Amplifier. तो यहाँ पर होना चाहिए इस region में. और this is the extreme end. Extreme end. Here it is act as a switch. That is the saturation region. It is on switch. Cutoff region. It is a off switch. The extreme end of the characteristics. And that is called what? DC load line. We are learning the concept of DC load line in case of analog circuit. So this is the elevated characteristics because of early effect. Right answer. What are the properties? Input resistance moderate, output resistance moderate, voltage gain moderate, current gain moderate or just high, but power gain is highest. Phase shift is 180 degree, most common and very popularly used configuration. सबसे ज़्यादा इस configuration का use किया जाता है. Then common collector. Common collector is what? Emitter follower. What is the another name of that? Common collector, emitter follower. Emitter follower means we are getting the output from emitter, we are giving input to the base, collector is common, and voltage gain is 1. Lowest voltage gain nearly equal to 1. And that's why emitter terminal will follow the input. That's why it's called emitter follower. Emitter follower. Its characteristics almost similar to what? Characteristics of common emitter. Because its output current is I. I is also equal to 1 plus beta times of IB. And in case of common emitter, IC is equal to beta IB. So almost same equation. IC or 1 plus beta, but somewhat more elevated because of this one. Somewhat more elevated as compared to common emitter characteristics because of this one, guys. Again, because of early effect. So this is the common collector. So common collector, what are the properties of the common collector? Highest input resistance. When we want very high input resistance, common collector is preferable. Then largest input resistance is mainly due to the feedback resistance RE, because its input resistance is given by HI plus 1 plus HFE times of RE. It is very, very high because of RE, and it is multiplied with HFE is beta. So sometimes if it is asked, you can give the input resistance like this. Input resistance HI. HI is nothing but 1 plus beta times of small RE from analog. And what is the RE? VT by IE. VT by IE. So 1 plus beta times of RE, 1 plus HFE times of capital RE. Because of that term, input resistance is very, very high for common collector. And this is also called emitter follower. Phase shift is 0. Output resistance is very, very low current gain is very high, 1 plus beta. Highest among the three configuration, 1 plus beta. Okay. So these are the characteristics, right? So it is another one. It is basically a current controlled voltage source. Emitter follower is analogous to voltage follower in operational amplifier. We are having the voltage follower in operational amplifier. In analog, I have explained this. This is called voltage follower. And source follower in FET. This is the source follower in FET. When we are taking output from the source, input to the base, input to the gate. This is called source follower, and it has the lowest power gain among the three configuration. Lowest power gain among the three configuration. Okay. Now, application of common collector configuration. What are the applications? Highest input resistance device, as an audio frequency power amplifier, as a buffer. Again, as a buffer. It is a voltage buffer because it is a voltage gain is what? 1. Because its voltage gain is 1, and it is an impedance matching device between high resistance and low resistance. Because its input resistance is high and output resistance is low. So it is an impedance matching device. That is called buffer. Voltage gain is 1 here. Now, acha, theek hai, tell me, up to this point any doubt, guys? Up to this point any doubt? Okay, chaliye. Just try to solve this question, and again we will take about 15 minutes break. Within this break, try to solve this question. It is a question from Milman Halkias. If alpha is 0.98, VB is 0.7 volt, find R1 in the circuit shown for an emitter current I is equal to minus 2 milliampere. Neglect the reverse saturation current. Beta is given, alpha is given, VB is given, emitter current is given. And now watch this question. This is the 12, this is the 3.3. R1 you have to find. R2 is 20 kilo ohm, it is given. RE is 100 ohm is given. This is the 2 milliampere current, it is given. But I is in opposite direction. So that's why it is the minus 2 milliampere is given. And now you have to find the value of R1. Right, VB is given as 0.7 volt. Okay. तो चलिए आप बनाइए. इसके बाद अब स्टार्ट करेंगे हम लोग next topic, that is the MOSFET and MOS capacitor, guys. MOSFET and MOS capacitor. Okay. So again, after this 15-minute break will start first of all, or just after break try to solve this question, guys. And you have to find the value of R1 here. This is RE, this is 20 kilo ohm, this is the 3.3 kilo ohm. Or tell me, what about the transistor? It is in which region? Cutoff, active and saturation. There is any idea? And why? So take break और आप भी आ जाइए फिर, क्योंकि अब स्टार्ट करेंगे MOSFET. क्या है भाई आंसर? That is very very wrong. Attractive status 5m. बताओ what is the answer? Vikram, Ashish Kumar. Now everyone join the session now. Now that is the third part. Okay. Now watch this question. First of all, this is the case. We have to find the 3.312 R1 and this is the 200 ohm, 100 ohm and 20 kilo ohm. Convert it into kilo ohm. R1 you have to find and R2 is 20 kilo ohm. Okay, if you are getting this type of questions, is it audible? Then this is VC, collector terminal voltage. This is the VB. VB is given as 0.7 volt. This current is IB. This current is IC, and what is this current? 2 milliampere. So IB plus IC is equal to 2 milliampere. IB plus IC is equal to 2 milliampere. Right now, as you know, what is the IC? This current is nothing but IE. IE is equal to IC is equal to alpha I, as you know. IC is equal to alpha I, but direction is given opposite. When the direction is given opposite, no problem. I is minus 2 milliampere. So then when the direction is opposite, it will become minus alpha I. Minus alpha I. Why minus? Because the current is given inside. So it will become minus 0.98 into minus 2. So it will become 1.96 plus. So that is the right current, 1.96 milliampere IC. So what is the IB will become? IB will become 2 minus 1.96. That is 0.04 milliampere. This is the value of the IB. No need to find the value of the beta. Now you have the value of IB, you have the value of IC. Why we are finding? Simply, just to find the value of R1, you have to find this current I1 and let this is the I2. And if VC minus VB upon I1 will give you the R1. You have to find the VC, you have to find the VB, and VC minus VB upon I1. VC minus VB upon I1 will give you the R1. Now you have the value of IC and IB. Then what is the value of VB? VB is nothing but 0.7 into 2 into 0.1. So VB will become VB plus 2 into 0.1, that is equal to 0.9 volt. This is the 0.9 volt. 0.7 plus 0.1, there is a 2 into 0.1, 0.9 volt. 0.9 divided by 20 will give you the value of the I2 because it is ground. So what is the I2? 0.9 divided by 20, that will become 0.045 milliampere. Now you have this current, So what is the value of the I1? I1 is nothing but IB into IB plus I1 is equal to I2 plus IB. So that will become 0.085 milliampere. You have to add these two values. 0.085 milliampere. Now you have the value of VB, you have the value of I1. Now what is the value of the VC? VC you can find 12 minus, what is this current? This current is IC plus I1. IC plus I1. So 12 minus 3.3 into IC plus I1 will give you the value of the VC. So what is the value of the VC? 12 minus 3.3 IC plus I1. Use your virtual calculator and give me the value. 12 minus 3.3. What is the value of the IC? 1.96. What is the value of the I1? 0.085. You will find the value of VC. Now use VC minus VB upon what? I1. Right? And then you can find the value here. Okay. So I think 51.2 kilo ohm. What is the answer here? 0.045, 0.85 is the value, and that is the point. VB is 0.9. You have to find only this value, VC. Then VB I have 0.9. This I have 0.085. And now find this calculation, put here, and you will get the value of R1. So that is the method. So how you are going to get the 141 ohm? This is 14 kilo ohm. Okay, no, 2.15 kilo ohm is also the wrong answer. I think this is clear to you. Second thing, when the collector is connected to what? Base. When the collector is connected to base, so collector is at higher potential as compared to base, and that's why the collector junction is reverse bias. Or when the collector junction is reverse bias and emitter junction is forward bias, it is in active region. This transistor is in active region, guys. Now, this is about the BJT. Next topic. Arey, kitna hai answer? How much is the answer? Okay then. Haber-Small model, that you have to revise that, and then guys, finally so before starting the next topic, that is what GATE 2024 score 15 out of 15 in general aptitude, exclusive on BYJU'S exam prep app, guys. So already that was taken by the Rakesh Talreja sir, and you can go through that. You can attend the recorded lecture also on, but you have to install what? BYJU'S exam prep app. BYJU'S exam prep app, first of all install and then follow this. Then 5.25, no, 5.2, 5.25 is the value of that voltage, and then 5.25, and then yes, R1 will become 5.25 minus 0.9 upon what? 0.085. That is the value. Okay. So you can find that around 51.2 kilo ohm. 51.2 kilo ohm. Now MOSFET, guys. अब देखो हो गया BJT, PN junction is done, semiconductor physics is done. Now MOSFET. देखो FET MOSFET means FET means what? There are three. One is what? JFET, but JFET is not in syllabus. So when the JFET is not in syllabus means what? MOSFET, metal oxide semiconductor field effect transistor, that is in syllabus. So it is a MOSFET. There are two types: depletion type, enhancement. But normally we are getting question from what? Enhancement type. E-type MOSFET, and again E-type there are two types, N channel and P channel. N channel and what? P channel MOSFET. Here depletion again N channel and P channel. BJT is called bipolar junction transistor because there is a current because of, yes, that is the right answer, 51.17 or 51.2 kilo ohm. Now in case of BJT, it is a bipolar, means current because of hole as well as electron, but it is a unipolar. It may be because of electron, it may be because of hole. That's why it is called unipolar device, MOSFET, metal oxide semiconductor field effect transistor. JFET is not in syllabus, so don't worry about the JFET. AC analysis already I have covered. That is the structure of three-dimensional figure. So three-dimensional, this is a P-type substrate. That is a N channel MOSFET, N positive, N positive. That is what is blue color is what? SiO2 layer. This is the gate terminal, this is the source terminal, that is the drain terminal, and that is called what? Width. W. Width, and this is called channel length. So if you have the idea about the width and channel length, then you can find the cross-sectional area of this portion. L into W or W into L. This is the area of this portion. And this is the N positive, it acts as a source, it acts as a drain point, and this is the P-type substrate. P-type means just for physical support. Similarly for N-type, वो है ना सर, डिप्लेशन MOSFET इज इन सिलेबस विक्रम, बिकॉज MOSFET इज इन सिलेबस. Metal oxide semiconductor field effect transistor, there are two types, E MOSFET, D MOSFET, both are in syllabus. So P positive, this is the N type substrate, source, gate and drain, right? Source, gate and drain. Here the current is because of holes, here the current is because of electrons. It is a three-dimensional figure. I think now it is clear to you. Now with the help of gate, try to understand, that is the structure here. What will happen? Source will provide the electron. Electron will move from source to drain and drain out from the drain terminal. So what is the direction of the current? Electron is moving from source to drain. So current will move from drain to source. That's why that is the arrow. And here we are having the SiO2 layer, that is called insulated gate field effect transistor. What will be the current here? Ig is equal to 0. And that's why it is called insulated gate field effect transistor. So that's why we are using the two layer. That is the drain terminal, that is the source terminal, and that is the symbol of what? N channel of P type body. Then channel is already created in what? D type MOSFET. Here there is no channel in E type of MOSFET. Then guys, there are three regions: cutoff region, linear region and saturation region. Linear region is also called, this is the special part of what? Triode region. Triode region. So in a cutoff and in linear region, it is used as a switch, on off switch, or in saturation region, it is used as what? Amplifier. It is used as amplifier. And if you want to design the voltage variable resistor, VVR, in which region it is designed as VVR? Tell me. In which region it is designed as voltage variable resistor? Everyone, give me the answer in comments box. There are three regions: cutoff region, linear region, saturation region. Then in which region it is used as VVR, voltage variable resistor, right? Then now this is the cutoff region, means when there is no channel, no, simply gate is connected to source, VGS will become less than 0. Or when the VGS is less than VT, VT is the threshold voltage, there is no channel, so there is no current. That is called what? Cutoff region. That is called what? Cutoff region. Yes, in linear region we can design what? VVR, voltage variable resistance. So this is the cutoff. Then in a cutoff region of MOSFET, or we can connect the negative voltage also. If suppose you are going to connect the negative voltage, negative will not attract electron, it will repel the electron, and that's why there is no channel between this and that. And that's why this is in cutoff region. We can put the VGS negative or less than threshold voltage. Then VGS is a small positive, again it will not attract any electron. When we are making the VGS greater than what? VT, then it will attract what? Electron. So that is what? P type substrate, we are making the VGS greater than VT. Now it will attract what? Electron. When it will attract electron, channel will induce between what? Drain and source, and current will flow from drain to source, right? And that is called, but in this case VDS is less than what? VGS minus VT, and that region is called triode region. That is called triode region. That is called what? Triode region, guys, right? Triode region. So this is a figure here. To triode region, we are having the uniform channel here, and we are connecting the VGS greater than what? VT, but VDS is less than VGS minus VT. In a triode region, we can design what? VVR. The formula for the current is given by K and S W by L, VGS minus VT into VDS minus half of VDS square. But remember, in this case, it is a VVR, it is a formula for the triode region. K and S is mu and COX. COX is the oxide capacitance, that is given by epsilon naught by QX. What is epsilon? R for SiO2? For SiO2, what is the value of epsilon R? Relative permittivity. Then when this is very, very small, so that you can neglect this term, then we are getting a linear relation, then it is called VVR. K and S, W by L, VGS minus VT into VDS. So what is the RDS, drain to source resistance? It is given by VDS upon IDS, and that is nothing but 1 upon K and S W by L VGS minus VT. This is called VVR. When we are changing the value of voltage, the resistance will change. Resistance will change. No, Vikram, that is not 11.7. What is the epsilon R for SiO2? 3.9. You are giving 11.7 for silicon. 3.9. So that is the drain to source resistance. And then in linear region, when we are increasing the VGS, resistance will decrease, slope will increase. So we are getting this type of shape. First, second, third, fourth, fifth. This is the reason. 1.5 volt, 2 volt, 2.5 volt, 3 volt, and so on. That is the case. This is called linear ohmic region. So we are increasing the VGS, resistance decreases, slope increases. This 1 by RDS is the slope of this curve. So this is called VVR. That is in special case of triode region. Special case of triode region when VDS is very, very small. So that is the VVR. Remember this formula. They will give you the direct question on this formula. And VGS minus VT is called overdrive voltage. VGS minus VT is called overdrive voltage, effective voltage. That is called VGS minus VT. VGS minus VT. It is called overdrive voltage or effective voltage, guys. Now, that is the case. Watch this. Linear region of MOSFET, right? VGS is greater than VT, VDS is less than VGS minus VT. There is an induced channel. I think it is visible to you. This is the VG. This is N positive, N positive. This is the induced channel here. This is the three-dimensional figure. Now it is in a horizontal direction, N positive, there is the channel, and that's why the electron will move from source to drain and the current will move from drain to source. Current will move from drain to source, and that's why when we are increasing the value of Vg, more electron will come. Concentration of electron increases, conductivity of channel increases because the conductivity depends upon sigma, N, Q, mu, N. What is the N? It depends upon the concentration of electron. More will be the VGS, more will be the concentration of electron, more will be the conductivity. Enhancement type MOSFET, right? And this is called inverted layer because initially it was P type, now it is N type. Now it is N type. So it is inverted from P type to N type. That's why it is called inverted layer. This is called inverted layer. Okay. Now, so this is the triode region. Now what will happen in saturation region? I think now this is a three-dimensional figure. Watch this. What it is clear. Clearly it is visible, guys. Throughout this there is a channel. It is a complete channel. Now, when VGS linear ohmic region it is over. This was the curve. Already I have given. This is the curve, different curve, ID versus VDS. MOSFET, channel pinch off. Channel pinch off means when we are starting increasing the VDS greater than or equal to what VGS minus VT, it will enter into the saturation. So exactly at VDS is equal to VGS minus VT, channel will pinch off. Channel will pinch off and transistor will enter into what? Saturation. Yes, 3.9, right answer. 3.9 epsilon R. And in saturation region, if you want to design what? If you want to design this type of channel we are getting, pinch off channel. This is called, it is pinch off towards what? Drain. It is pinch off towards drain. It is uniform. It is remains same towards what? Source. That is called pinch off channel. That is the pinch off, completely pinch off. That is called tapered shape. This is the tapered shape channel, and finally it is a pinch off channel, guys. It is visible to you, everyone. This is called pinch off channel. Now, this is front view, uniform channel. tapered shape, finally pinch off. Once it is pinch off, at pinch off point, VDS is VGS minus VT, and the current will become half of K and S W by L VGS minus VT the whole square. VGS minus VT the whole square. Okay, then that is the case. Watch this, guys. This is the characteristics. Once the channel is pinch off, there is a bending of the curve, and finally it will enter into the saturation. And at this point, VGS minus VT, or if it is greater than VDS, again that is it will enter into the saturation. We are increasing the VDS, but there is no change in the current ID. So that is called what? Three-dimensional figure and characteristics. First, in this region, when the VDS is very small as compared to VGS minus VT, this is called linear ohmic region. Then this is called bending of the curve, and finally it will enter into the saturation. So important part is characteristics. Okay. Now there are two characteristics. One characteristics is what? This is called output characteristics, ID versus VDS. VDS. This is called output characteristics. Remember that word is important. Why output? ID is the output current, VDS is the output voltage. That's why it is called output characteristics. And that is called what? Transfer characteristics. Transfer characteristics. Transfer characteristics means what? ID versus VGS. We are increasing the VGS, there is a negligible current, and suddenly the current will start increasing, and that is called VT, threshold voltage. After threshold voltage, it will increase like this, square law. It will follow the square law, right? Yeah, how to calculate the what value of that? Okay, VGS cutoff in case of depletion type MOSFET. So, just we are finding, actually what we are doing in case of JFET, we are finding how to find the pinch off voltage. That is the method here. Now, this is the small signal model, guys. Under saturation, when we are using the common source, this is the source, this is the source, this is the gate terminal, this is the drain terminal. Source is common. We are giving input to the gate. Why it is open circuit? Because the input resistance is infinite. But current depends upon this VGS in a saturation region, because current is given by what? 1 by 2 K and S W by L VGS minus VT the whole square. You can find the GM from this formula. You can differentiate with respect to VGS, and you can find the GM K and S W by L VGS minus VT. VGS minus VT. Now watch this. VGS, this is the GM VGS, RD. RD is the drain resistance. RD is called drain resistance. GM is the transconductance. Now why we are getting the RD? Again, there is a one phenomena in this, that is called what? Channel length modulation. Because of the channel length modulation, that curve is somewhat elevated, actually not at a straight. In a saturation region, again there is a change in the current because of the change in VDS. And what is the slope of this line? 1 by RDS. 1 by RDS, and that is the drain to source resistance, or this is called RD only, drain resistance. And this is because of early effect of channel length modulation. That's somewhat elevated in saturation region, and that's why we are having the two currents. One because of the VGS, and there is a change in the current because of the VDS upon RD. So that is the formula for ID, GM VGS plus VDS into RD. So in EDC, they will ask, find the transconductance, that is the GM, and then find the GD, change in ID because of change in VDS. You have to find this. That is the formula. Now, and that is the small signal model. We are already in my session in analog. I have solved number of questions. If you have just want to get the idea, then please watch that my session, analog in one shot. At the starting point, I have given the everything about the MOSFET. Starting point, everything about the MOSFET, guys, about the small signal model, how to use the small signal model, what are the characteristics and so on. Now, there is another model. This is called low frequency model. Now, it is a high frequency model. When we are talking about the high frequency model, we have to consider all the capacitance. That is the capacitance between gate and drain, CGD. That is the capacitance between gate and source, CGS. That is the capacitance between drain and source, CDS. So this is called high frequency model. At a low frequency model, this will act as open circuit, this will act as open circuit, this will act as open circuit. In low frequency model, no need to consider the internal capacitance, but at a high frequency, you have to consider the internal capacitance. These are called internal capacitance of this. So in a capacitor, MOS capacitor, I will give the standard formula for all this. Now, that is the channel length modulation in 3-dimensional figure. Watch this. Channel length modulation means, according to channel length modulation, what will happen when we are increasing the VDS more than what VGS minus VT. This VGS minus VT is called VD set. When we are applying the excess voltage, this pinch off point is moving away from the drain towards source. This is pinch off point. Away from the drain towards source, it is moving. Right towards what? Source. And that's why this is depletion region. And this will become very high field region. This will become what? Very, very high field region. When the electric field will increase, drift velocity will increase. That's why the current will increase. So because of this channel length modulation, length of the channel will reduce. When the length of the channel will reduce, what is the resistance? Rho L by A. If the effective length of channel will reduce, resistance will reduce, current will what? Increase. That is called channel length modulation. The pinch off point is moving away from the drain towards what? Source. So that is called channel length modulation, guys. Now, because of this channel length modulation, curve is what? Elevated, guys. Curve elevated. Somewhat elevated. And then, what is the formula here? This is the formula when we are considering the channel length modulation. Half of mu and ux, this is called K and S. W by L is called aspect ratio. VGS minus VT the whole square. Up to this, that is the formula for saturation region. When we are adding the 1 plus lambda VDS, this is for saturation region. This is for channel length modulation. Where lambda is called 1 by VA. VA is the early voltage. So what is the unit of this? Volt negative. Volt negative is the unit of this. 1 plus lambda VDS. To account for the channel length modulation, we multiply the channel length modulation coefficient assuming L is constant. Right? That is what? This is the just base width. Base width modulation, it is a part of BJT, and channel length modulation is a part of what? FET. No. As is not similar phenomena. They are different phenomena, because in case of BJT, base width will change, or in case of FET channel, both are called early effect. And because of both phenomena, current will increase, no doubt. In one case, IC will increase. In other case what? ID will increase. Okay. Both given by what? JM early. That's why this is called early effect. Here lambda is called early effect coefficient. Any other doubt? Any other doubt? और भी कुछ पूछना है तो पूछ लीजिए, फिर आगे बढ़ते हैं. Now, Sir, BJT, how the current equation will change based on the early effect? Current equation actually in model we are using now. In model, in H parameter model we are using, or otherwise alpha will change. This is the model. Why we are having this term? This is because of early effect. Why we are having this term? Because of the early effect. And sometimes in model, for example, hybrid pi model. R pi, V pi, GMV pi, and we are using one R naught here, and that is because of early effect. What is the IC? IC is given by GMV pi plus what? VCE upon R naught. This is because of early effect. This is because of early effect R naught. What is the R naught here? We can say VA upon ICQ. VA is the early voltage, ICQ is the DC current, and in this way we can find the output resistance. That is the logic of early effect in case of BJT. Okay. Up to this point it is clear? 1 minute. Okay, ये है, this is the QR code guys. You can scan this QR code. Okay, everyone scan this and you can join what? Mock test, and then you can continue with that mock test guys, and try to give as many mock tests as possible, but minimum 3 to 4 mock tests, full length mock test, so that you will get the idea and you will get the command over time management with virtual calculator and what? Scribble pad. उसके बिना मत देना, वर्चुअल कैलकुलेटर लो, स्क्रिबल पैड लो, और जैसे एक एग्जाम होता है ना वैसे दीजिए। और कितने लोगों को डर लग रहा है रिजल्ट्स के बारे में सोचकर? डरने की कोई जरूरत नहीं है, बस सोचो मत रिजल्ट के बारे में। जो आप रिवीजन कर रहे हो ना उसको रिवीजन करते जाओ। देखो आप पूरा 4 घंटे के अंदर पूरा ईडीसी 5 घंटे में जब आप खुद करोगे ना तो 2 से 3 घंटे में आप पूरी चीज रिवाइज कर लोगे। और अगर आप ये नोट्स चाहते हो तो आप मेरा टेलीग्राम चैनल ज्वाइन कर लीजिए, वहां से आप नोट्स ले सकते हो। पहले इसको स्कैन कर लीजिए अपने मोबाइल पर, तो ये आपको मिल जाएगा कि क्या डिटेल है इसके बारे में। ओके, अब देखो, अब मैं एंटर कर रहा हूँ व्हाट? कैपेसिटेंस के ऊपर। जो मॉसफेट का तो मैंने डिटेल बताया है आपको एनालॉग में, कैसे यूज करना है, कैरेक्टरिस्टिक्स क्या होती है, अर्ली इफेक्ट क्या होता है। मेन जो आपका क्वेश्चन आता है ना मॉस कैपेसिटर पर ईडीसी में, अब वो देखते हैं ईडीसी में मॉस कैपेसिटर कैसे आएगा। तो सबसे पहले देखो जंक्शन कैपेसिटेंस है, दैट इज कॉल्ड व्हाट? सोर्स बॉडी कैपेसिटेंस गाइस। सोर्स बॉडी कैपेसिटेंस मतलब ये बॉडी है, there is a capacitance P n positive junction, P n positive junction. This is called source drain body junction, source body junction. It is just like a depletion capacitance. So, today I have given you the formula of the diffusion capacitance, transition capacitance. So what is the transition capacitance? Already I have given a CT2 upon CT1. That is nothing but root over built-in potential plus what? Reverse voltage VR1, V0 plus VR2. Now this time the VR1 is this is N positive, this is the body, this is N positive, this is the source, this is the VSB. VSB is nothing but the VR. When I am putting the VSB 0, that capacitance is called C CSB. This is called CSB. This is called CSB0. CSB0 means VSB. When the VSB is 0, it is given by, when this VR1 means VSB1 is 0, it will become V0 upon V0 plus when VSB is applied. Now, so what is this? You can arrange this formula and you will get source body capacitance is given by source body capacitance when there is no reverse bias voltage upon, this is divided, it will become root over 1 plus VSB upon V0. V0 is the built-in potential. V0 is the built-in potential. Vt log of Na Nd by Ni square. This is the formula, guys. Okay. Then here it is the formula. This is the, you can understand. Similarly, you can write for drain body capacitance. Similarly, you can write for drain. Remember, it is just like a depletion capacitance. It is just like a depletion capacitance. This is the drain body capacitance, guys. In place of source, you have to use the drain only. This is again a depletion capacitance, and we have to keep source body junction and drain body junction reverse bias so that there will be no current in vertical direction. Only there will be the current in horizontal direction from drain to source or source to drain only, not in opposite direction, not in vertical direction. Okay. Then this is, there are two capacitance. Then another one is what? We have to deal with what one characteristic, that is called what? CV characteristics. CV characteristics means C versus VGS, and we are having the three different mode. One is called accumulation, one is called depletion, and one is called what? Inversion. Accumulation, depletion and inversion, that is the change in charge because of change in voltage, that is called the capacitance characteristics. And what are the modes here? One mode is called accumulation mode, one mode is called depletion mode, one mode is called inversion mode. Accumulation mode means when we are applying the negative voltage at this point, when we are applying the negative voltage at this point, 1 minute, at this plate, when we are applying the negative voltage, then it will attract what? Holes, and there is an accumulation of holes at this point. When there is an accumulation of the holes, so here it is a positive charge, here it is a negative charge, it behaves like a capacitor, and that is called oxide capacitance. There is only oxide capacitor, and that is called what? Accumulation mode. So accumulation mode means we are giving the highly negative voltage VGS, it will attract holes on the plate. One side it is negative charge, one side it is positive charge, and that is what in accumulation mode, and that capacitance is just equivalent to what? Oxide capacitance. Or remember what is the oxide? 3.9 epsilon naught upon TOX, where TOX is the oxide thickness. TOX is the oxide thickness. चलिए बताइए जरा, ये क्लियर है सबको? This point, right? So this is a very important one, accumulation mode. Then second mode is what? Second mode is depletion mode. In depletion mode, actually we are applying a positive voltage here, less than or equal to Vt. What will happen? First of all, it will repel the holes. When it will repel the holes, we are having only immobile charge carriers like this. Immobile charge carriers. So what about depletion width increases? When the depletion width will increase, there will be two capacitance. One because of oxide and one because of this semiconductor, or width will increase. Or when that will be the case, guys, that will be the case when the width increases. This is the width increases, depletion width increases. Because of that, two capacitance will be in series. Oxide capacitance and depletion layer capacitance will be in series. And when the two capacitance are in series, always remember overall capacitance will reduce. Two capacitance in series means overall capacitance will reduce. So when it is in depletion mode, capacitance will decrease, and there are two capacitance in series, and that's why we are having the formula. In a depletion mode, what are the capacitance? One because of the semiconductor and one because of the oxide. inside the semiconductor. What is the oxide capacitance? That is given by epsilon naught x by TOX, oxide thickness. This is the 3.9 epsilon naught upon oxide thickness. That is fixed value. But what is the semiconductor capacitance? That is given by epsilon s by omega or W. W is the depletion width. What is this? Epsilon r epsilon naught, that is 11.7 or 12 for silicon, or W is the depletion width. It is variable. We are increasing the voltage, depletion width will increase. Now, when the voltage is Vt, exactly maximum voltage Vt, then VGS is Vt, then depletion width will reach to its maximum. That is called XDT. When it will reach to maximum, this will reach to minimum. Semiconductor capacitance, that is given by epsilon naught epsilon r upon XDT. This is called maximum depletion width. Capacitance will reduce. Overall capacitance will also reach to minimum. That is called minimum capacitance. In depletion region, that is called minimum capacitance. Always use this formula. Upon what? C minimum, CS minimum. CS minimum, guys. So that is a very, very important formula. What is the overall minimum capacitance? That is the series combination of oxide capacitance and minimum capacitance, guys. Okay, so we have to solve the number of questions on this minimum capacitance. What is the ratio of the maximum capacitance and minimum capacitance? What is the ratio of the maximum and minimum capacitance you can find? You can write here. For example, this is the C minimum. What you can write C minimum? This will become COX plus CS minimum upon COX into CS minimum. And what is the maximum capacitance? Maximum capacitance is nothing but COX. So maximum capacitance possible is COX. Minimum capacitance, 1 by minimum capacitance, we have find COX plus CS minimum upon COX C minimum. Guys, multiply these two equations. When I am multiplying, you will get C maximum upon C minimum. When I am multiplying this COX is cancelled out. This COX is cancelled out, and you will get the ratio upon C minimum. Now, divide it, so you will get 1 plus COX upon CS minimum. Now, what is the COX? Epsilon naught x by TOX. And what is the CS minimum? Epsilon S, that is the semiconductor, upon XDT. XDT is the maximum depletion width. So guys, you can put here and you will get very, very important formula. Remember, epsilon x by epsilon S into XDT upon TOX. So that is the ratio C maximum upon C minimum. That is the ratio. More will be the depletion width, more will be the ratio. So that is the, directly you can use this formula. If you ask what is the ratio of the C maximum and C minimum, directly you can use this formula. Directly you can use this formula. Okay. So this is a very, very important one. C maximum and C minimum. The minimum capacitance, that is we are getting in minimum capacitance in depletion mode. And finally there is a inversion mode, guys. There is a inversion mode. In inversion mode, what will happen? We are giving what? Positive voltage here. When we are giving the very high positive voltage here, it will attract what? Electron, and P type is converted into what? N type. When the P type is converted into N type, then it is called inversion mode. And again we are having what? Oxide capacitance, because on the one side of the plate there is a positive charge, on the other side of the plate there is a negative charge, and that is called what? That is called inversion. That is called what? Inversion. So we are having the two characteristics. like this. Remember guys, it is a quick revision. So if you have idea about the subject, then you can understand this is just a quick revision within 5 hours or 5 to 6 hours. And 2000, if you want to start your preparation for 2025, then that is not the platform, because it is a this is not the session for 2025. It is 2024 quick revision, guys. So here we are having this type of characteristics: accumulation mode, minimum capacitance, and that is the case. Tell me, it is a high frequency response or low frequency response? This is the VT, and here we are having the minimum capacitance. Already I have given you the formula, and that is the C versus VGS. And that is the COX. That is the COX. Oxide capacitance, maximum capacitance, and this is the minimum capacitance. This region is called accumulation. From this point to this point, accumulation. This is the accumulation. After that, depletion is started, and VT we are getting the minimum, and that is the inversion, and this is called strong inversion. Strong inversion, and it is a low frequency response. It is a low frequency response. Now, at a high frequency, what will happen? Up to this point, accumulation, depletion will remain same, but for high frequency, this curve will be straight line. High frequency means it is in the range of megahertz, or it is in the range of what? Only hertz. So this is the low frequency response. In low frequency response, that will be the curve. On high frequency response, that is the curve. So normally when we are getting the question on high frequency, they will provide you this type of characteristics in numerical. In particular numerical, they will provide you this type of characteristics. This type of characteristics. Okay. So that is the numerical. Okay. तो ये है प्रॉब्लम. अब इसको आप देख सकते हो. ओके then. ये होगी characteristics. Frequency effect means what? In high frequency, what will happen? There is no strong inversion. This is, we are getting the minimum capacitance here at VT. Minimum capacitance at VT, and then it will not change. And this is the oxide capacitance. This is the minimum capacitance. So we are getting question on this diagram. Be careful. And they will normally talking about what body type. Which type of body? If that is VT is positive, means it is a N channel. VT is positive means it is N channel, but body is P type. Body is P type. Remember, in N channel, body is P type. This is N plus, this is N plus, and that is what? P type. This is what? P type. Okay, that is the case. Now, तो भाई किस टाइप के क्वेश्चंस आएंगे ये देखो जरा. दैट इज अ वन क्वेश्चन. MOS capacitor made using p-type substrate is in the accumulation mode. The dominant charge in the channel due to the presence of. अब यहाँ पर देखो, sir, for the MOSFET flat band voltage is always negative or it can be positive. अभी बताता हूँ मैं, flat band voltage का फॉर्मूला देता हूँ मैं आपको. For MOS capacitor made using the p-type substrate is in the accumulation mode. The dominant charge in the channel is due to the presence of. देखो यहाँ पर क्या लिखा है? MOS capacitor made using p-type substrate. P-type substrate means it is a N channel. Or in accumulation mode. Accumulation mode मतलब means what? We are accumulating the whole here. This is the accumulation of hole in this region. Hole. The dominant charge in the channel is due to the presence of holes. This is called channel. P-type substrate, it will attract the holes. That is the channel, guys. So this is this type of questions we can expect. Some questions on Fermi level, there may be the chance of the Fermi level. Bending of the curve like this. अब आपने क्या क्वेश्चन पूछा है? For example, that is the question, guys. Now, for me, energy band diagram of the MOS capacitor, you have to revise this. Energy assist, you have to revise the energy band diagram. Energy band diagram means, देखो, actually far away from the, this is what gate terminal, this is the SiO2 layer, this is the metal, this is metal, this is SiO2 layer. What is the thickness of SiO2 layer? TOX. Now far away from the junction, watch this, the Fermi level is near to EV. Watch this, Fermi energy level is near to EV, and then EFI. EF is below the EFI, and that's why it is a P-type substrate. It is P-type. P-type means it is a N-channel MOSFET. Okay. Now watch this. Here, EFI, EV are moving. Watch this. EV is moving away from the Fermi level. When the EV is moving away from the Fermi level, and now at this point, EF is above the EFI. EF is above the EFI, means this is converted into what? N-type. Because in that case, the Fermi level is near to what? Conduction band. Watch this, near to conduction band. This is the EC, this is the EF, and EF is near to conduction band above intrinsic Fermi level. That is called banding of the curve, and because of that we can say it is, this region is N-type. So it is converted from P-type to N-type, and that's why it is called inversion layer of the electron, and that is called, it is in inversion mode. It is in inversion mode. Okay. Okay, Rajesh, how are you? So chaliye, this is the large positive voltage. So when we are giving the large positive voltage, it will attract the electron, and that's why there is a banding of the energy level, and P-type is converted into N-type, and that is called what? Strong inversion. Means when it is moving downward, when it is moving downwards means everything is moving away, then it is what? P-type, P is converted into what? N-type. That is called what? Inversion. Or suppose it is moving upward, and that is called what? Accumulation mode. That is called what? Accumulation mode, guys. Watch this diagram. Watch this diagram. This is the accumulation. When there is a bending of the curve, EV is moving near to what? EF, means more holes are accumulated here, and that's why the distance between the EF and EV is reduced. That is called what? Accumulation. And that is what, this is not inversion, this is not inversion, that is what? Depletion mode. Because when the EFI will become, EFI will goes downward and below EF, then it is called inversion, but just bending of the curve. So that is called depletion. That is called what? Depletion mode. This is called what? Accumulation mode, and that is called inversion mode. So this diagram, this is the strong inversion. Yes, that is the strong inversion in this diagram. There are three cases with the Fermi level, guys. Then get the command over that. This is where, or you can compare with this all the three diagrams on the same table, right? And now watch this. EF is near to EC. EF is near to EC, far away from the junction. That is, the body type is N-type. If body type is N-type, means it is a P channel. Now it is a P channel, guys. Now when it is moving downward, means the gap between EC and EF reduces. Gap between EC and EF reduces, means there is an accumulation of the electron in this region. So positive voltage is applied, it will attract the electron, and that is called accumulation mode. When small negative voltage is applied, that is called what? Depletion. It will repel the electrons away, and that's why the distance between EC and EF decreases. That's why this will become just like an intrinsic type. And after that, when we are giving very, very large negative voltage, EF and EV, the distance is very less, EF and EV. That's why N-type is converted into P-type, and that is called what? Strong inversion. And large number of holes are collected here. That is called bending of the curve. So these three diagrams are very, very important. Please compare, because directly we are getting question, 2 mark question, match the following, MSQ and so on. So that is the case. Now, finally, we are getting one question on what this one, threshold voltage. Here, this you asked what is the flat band voltage? This is the flat band voltage, guys. So threshold voltage is given by phi ms. Phi ms is the work function of metal minus work function of the semiconductor. Normally, this term is what negative because phi m is less than phi s. So this term is negative. Okay. Qi upon Ci. What is the Ci? COX. That is called oxide capacitance. Epsilon naught x by TOX. This is the oxide capacitance. What is the Qi? Qi is nothing but Qx. That is the charge trapped inside the oxide. Okay. So Vikram, you asked one question. What is the flat band voltage? The charge trapped inside the oxide. Now, normally the charge trapped inside the oxide, it is positive. Because there is a cleaning and so on. So Na positive charge, this is the oxide, and charge inside that, this is the positive charge is trapped inside the oxide. Normally. So when the positive charge is trapped, this is positive, but it is a negative. So this is also negative, this is also negative. So what about the flat band voltage? Normally we are getting the flat band voltage phi ms minus Qx upon Cux. This is negative. This is negative. But it may possible that this term is 0, so flat band voltage may be 0. Right? That is what this is. There is no oxide capacitance. We are assuming that work function of metal and work function of semiconductor are same. That under ideal condition, flat band voltage will become 0. Otherwise, it will be negative. Now, QD by COX. QD is what? Depletion layer charge. Depletion layer charge means here we are having a depletion layer. So this is the N positive. This is the N positive. This is the depletion layer. Right? That is called depletion layer charge. So suppose we are talking about the N positive. This is the body is P type. N channel or P type substrate. So what is this depletion layer charge? It is also negative. Watch this. This is negative, 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 negative. So this is a negative charge. But when we are putting the QD negative, this negative, what will be? This negative will become positive. This negative and that negative will become positive. So watch this. So QD is negative. Ci is nothing but COX. So that is. Now finally 2 phi f. So Vt log of Na by N, that is the phi f function. It is given here, formula. Now, so ultimately, overall threshold voltage, it is positive value. You can find, this is the value here, 2 phi f. 2 phi f is given by Kt by Q. Kt by Q is nothing but Vt. If it is in voltage, it is required Vt log of Na by Na. Vt log of Na by Ni. This is 2 times of that, Vt log of Na by Ni. That is called for inversion. That is required for inversion, guys. So that is the complete threshold voltage. We are getting question on this formula, guys. Please prepare this formula. Okay, this is a very, very important one. 2 Vt log of Na by Ni. This is positive, that is positive. This may be negative, but overall threshold voltage may be positive. Sometimes what will happen? क्या negative voltage possible है क्या? Is it possible that we are getting the negative threshold voltage? Yes or no? In case of N channel, if it is possible, there is a negative voltage. Yes, it is possible. If it is very, very low, doping is very low, this doping is very low, then this is negative, this is positive, but it is very, very low. So overall value may be negative. Overall may be negative. No, that is, I am not talking about the depletion. It is, I am talking about the enhancement, Vikram. In enhancement type, again, the threshold voltage may be negative for N channel. Watch this. This is the threshold voltage. Here the threshold voltage is negative. But when I am increasing the doping of P type body, then it will become 0. And after that it will become positive. So normally when we are solving the question, what is the VT? VT we are assuming positive for what? N channel. And negative for what? P channel. But it may be negative for N channel when the doping is very, very less. After that it will become 0 and finally it will become positive. So normally we are dealing with in this region, that's why we are taking positive, otherwise it may. But for P MOSFET, P channel MOSFET, it is always negative. P channel MOSFET, it is always negative. More will be the doping, more will be the negative. Why? Because this term is always negative. Whether it is a P channel MOSFET or N channel, these terms are negative. And for P channel, this is also negative. QD, because it is a QD is negative. Why QD is negative? This term, this is negative now. Or what is the QD for P channel? In P channel, body is N type. P positive, donor ions. So when we are putting donor, it is a positive, but what is the sign here? Negative. So these two terms are negative, this is negative, overall value is negative, and that is only, this is one, this is the factor here. Okay. So when we are increasing, overall value is negative for P channel, positive for, it may be negative or positive for N channel. So that is a very, very new diagram for you. Okay then. Now, तो ये इतना आपको बनाना है भाई थ्रेशोल्ड वोल्टेज पे. वी आर गेटिंग द नंबर ऑफ क्वेश्चंस ऑन दैट. Already in my session I have solved number of questions. You can watch, guys. And then this is the schedule for mock test, that is from 13 January to 19th of Jan. So first of all, install the BYJU'S exam prep app with the QR code, and then guys, mega mock test will be open for you. You can register here on our BYJU'S, and that is the schedule for your test. 65 question, 100 marks, 180 minutes. For EC branch, okay, and you have to give minimum 3 to 4 mock tests before exam. So that is for you. Okay. And now in MOS capacitor, remember we are getting different types of questions. That some practical questions are what this like this. For a MOS capacitor biased in accumulation mode, the effective capacitance is. In accumulation mode, the effective capacitance is only oxide capacitance. This is the formula for depletion region. Two capacitance are connected in series and so on. Okay, so that answer is B for this. Answer is B for this. So this type of questions we are getting in, right? So please solve all that type of questions. Then I have given you the idea about the threshold voltage. All in my number of sessions I have solved questions, guys. Already I have given you the characteristics. Right, and then थोड़ा सा ना डिप्लेशन मॉसफेट भी थोड़ा सा तैयार कर लीजिएगा. डिप्लेशन टाइप ऑफ मॉसफेट. जस्ट आई एम गोइंग टू गिव यू द सम हिंट अबाउट द डिप्लेशन टाइप ऑफ मॉसफेट. 1 minute. What is the depletion type of MOSFET? I am going to explain you. Or in my analog class already I have solved number of questions, guys, right? So please solve those questions. Watch this. In depletion type MOSFET, actually we are having extra channel here. It is N type, N positive, N positive, and this is P type body, right? Now already there is a channel. Already there is a channel. So when we are applying the VGS, we can apply the VGS negative as well as VGS positive. When we are giving the VGS negative, it will repel the electron. When it will repel the electron means what about the conductivity of channel? Reduces, and that is called what? Depletion mode. can take the, what you can take, what CPF as a VGS means flat band voltage. Now this is a depletion type MOSFET, same, but only there is a difference. We can apply the VGS as well as VGS negative as well as positive. When we are giving the negative, it will repel the electron. When we are giving the positive, it will attract the electron. Conductivity of channel will increase, conductivity of channel will decrease. So what is the change in the characteristics? When VGS is 0, again there is a current. When the VGS is 0, again there is a current. And when we are making VGS negative, it will reduce like this. When we are increasing the VGS, it will increase like this, current will increase. And this current is called IDSS. Drain to source saturated current when VGS is equal to what? 0. When we are giving the VGS positive, that is called enhancement mode. Here it will work like a E-type MOSFET, or we can also apply the negative VGS. And at particular point, this will become VGS cutoff, where the conductivity of channel will become 0. This act like what? VTP. VT, threshold voltage. Means we can say the threshold voltage is negative for this. We can say the threshold voltage, actually it is a VGS cutoff. When we are giving the negative voltage, finally the conductivity of channel will become 0. And that is called VGS cutoff, guys. So it is the IDSS is called drain to source saturated current when the VGS is equal to 0, guys. So we are using, this is the VGS cutoff. So you can use the same formula here. What are the formula for saturation? IDS is equal to half of K and S W by L VGS minus VT the whole square. Now remember, how you can get the value of the VT? VT is nothing but VGS cutoff. It is negative value. Cutoff. Remember, this is the negative value. Now, exactly when VGS is 0, what is the current? Saturation current is IDSS. You can put the IDSS here. And it will become half of K and S W by L. This term is 0. This term is 0. So it will become VT square. That is the formula for IDSS, guys. IDSS, very important one. You can use this formula. So normally they will give question like this. From this you can find the constant. What are the constant? K and S W by L. So what is the K and S W by L? You can say the K and S W by L is equal to 2 times of IDSS upon VT square. Now VT is sometimes it is called pinch off voltage. So we can put here. So this formula will become IDS is equal to this 2, that 2 cancel out. IDSS upon VT square VGS minus VT the whole square. Now put inside, you will get the well known formula IDSS 1 minus VGS by VT the whole square. Because inside the root it will become VT, 1 minus VGS by VT the whole. It is negative, it may be negative, positive, it is negative. If it is negative, it is negative, negative, negative cancel, it will become overall value positive will become. VGS may be negative, may be positive, but remember VT is negative. VT is what? Negative, guys. So that is the case. In this way we can solve the question. That is the standard formula for junction field effect transistor, JFET. We are getting the same. But you can use the same formula here. But here remember what is the IDSS, because in some numerical they will give you the value of IDSS. कौन से स्टेशनरी में मिलेगा ये बताओ? जाऊंगा और क्या करूंगा? पहले पूछ लो, नहीं मिलेगा तो फिर तुम क्या घर से निकलोगे? इतना भीड़ है यहाँ पे, जाना पड़ेगा। क्या है ना, आज ना गड़बड़ हो गई यार, कुछ खाया नहीं है वो, और कुछ दिक्कत नहीं। सब ठीक चल रहा है, एक तो तंग कर दी क्लास, कहाँ कहाँ 4 बजे खत्म होनी थी यार, देख सब रूटीन मेरा गड़बड़। हेलो 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 हेलो, इज इट ऑडिबल? ना चलो कुछ लास्ट के पॉइंट्स रिवाइज कर लेते हैं। फाइल का थोड़ा करप्ट हो गई है, राइट। आई थिंक इट इज ऑडिबल गाइस। वो तो क्या, ऑलमोस्ट मॉस्फेट इज कवर्ड नाउ। अब उसको रिकवर करके आपको सेंड कर देंगे ऑन टेलीग्राम चैनल। बट अभी तो ये प्रॉब्लम है कि फाइल आ नहीं रही है यहाँ। यस गाइस, नाउ तो देखिए जरा। अब देखो लास्ट में ना, दैट इज इन मॉस्फेट देयर इज अ वन इंपॉर्टेंट क्वेश्चन इन ईडीसी, दैट इज कॉल्ड बॉडी इफेक्ट। व्हाट इज द बॉडी इफेक्ट गाइस? In IC, the body terminal should be connected to the most negative supply first thing. Due to reverse bias junction, depletion layer width increases and hence it increases the threshold voltage. So there was a one question in threshold voltage. Vt is given by Vt naught. Vt naught means when the VSB is 0. That is the gamma factor 2 phi f plus VSB minus 2 phi f. What is this? Threshold voltage for VSB is equal to 0. This is the VSB. Okay. That VSB is equal to 0. Then you can give that formula. Then okay, and then physical parameter, that is given the value here. This is a very important formula to find the threshold voltage, and that is called what? Body effect. Is it audible? Okay then. Now so please get the command over this formula guys. This is also very important one. Then temperature effect, threshold voltage Vt and K dash are temperature sensitive. Vt decreases by 2 millivolt for every 1 degree rise in temperature, and then K dash decreases with increase in temperature. So when temperature increases, there will be two effects. Mobility decreases, temperature increases, Vt decreases. So because of that, current decreases, and because of this, current increases. But this effect is dominant, and that's why when the temperature increases, current decreases. And therefore, remember guys, what will happen? There is no chance of thermal runaway in case of FET. That is the biggest advantage of what that FET. Okay, so this is the one of the advantage. The temperature increases, current decreases. There is no chance of thermal runaway in that case. That is called temperature effect. Now, I want to just give you the idea about what special diodes. So what is that? I'm going to explain you. Then 1 minute. This is in special diodes. We have solar cell. First prepare this. Already I have given you the idea about the varactor diode. Then what another is what Jenner mechanism and avalanche mechanism. Avalanche mechanism, and then already we have discussed the varactor diode. Then LED, basic idea about the laser. Okay, so these are the points. So these are the important things. Jenner mechanism, and what is the difference between the Jenner mechanism and avalanche mechanism, you have to consider. So just give me 1 minute. Now, first of all, already I have given you the idea about what varactor diode, that is called voltage variable capacitor. So it works in what? Reverse direction. Already I have given you the equivalent circuit for that. So this is the varactor diode or varicap, variable capacitor, voltage variable capacitor. We are getting this type of characteristics. Exactly at when VR is 0, we are getting the maximum value of the capacitance. This is the maximum, and then this is the maximum when 0, and when we are giving the VR negative, it will reduce because capacitance is proportional to Vj raised to power minus 1 by 2. Here Vj is V0 plus VR. Okay, varactor diode. Then voltage controlled oscillator, frequency and phase modulation. It is the applications of the varactor diode. Then guys, Zener diode. Zener diode we are using as a voltage reference. Means once in reverse direction, once the diode is breakdown, it will provide a constant voltage. So in analog we have discussed voltage regulator by using Zener diode, right? But there are two mechanisms. One is called avalanche mechanism, one is called Zener mechanism. So what is the difference between the avalanche and Zener mechanism? Zener mechanism means direct rupturing of bond, and avalanche mechanism means what? Chain reaction. Second important thing, Zener occurs at what? Low voltage, and avalanche occurs at high voltage. For Zener, the doping is very high on both the sides. P side doping is high, N side doping is high. But for avalanche, doping is moderate. And Zener, in case of Zener, it has negative temperature coefficient. Means when the temperature increases, breakdown voltage decreases. But in case of avalanche mechanism, it has the positive temperature coefficient. So these are the difference between the Zener mechanism and avalanche mechanism. Avalanche mechanism is impact ionization, or Zener mechanism means what? Direct rupturing of bond, guys. So you have to clear these points. That is the difference between Zener mechanism and avalanche. And what about the applications of the breakdown diode? You will find application in analog. In case of voltage regulator by using Zener diode, voltage regulator by using op-amp and Zener and transistor. So this type of applications. Okay, it is used as a constant or reference voltage. So Zener diode is heavily doped PN junction. It is designed to conduct in reverse direction when certain specific voltage is raised. And that is the characteristics of Zener diode. These are the characteristics like this. Once it is breakdown, the voltage will become constant in reverse direction. And what is the symbol for the Zener diode? That is the symbol for the Zener diode. This is the Zener diode, guys. Now, these are the characteristics. It works in reverse direction, guys. So that is called a breakdown voltage, BZ. In forward direction, it behaves like what? Normal diode. That is the drop across the diode, and this is the breakdown voltage. Now, that is the what? P positive, N positive energy levels. Here it is the EC. Here it is the EF. Here it is the P positive type. This is the N positive. Both P positive and N positive. Doping is very high, and it works on what? Tunneling phenomena. Because of the doping, depletion layer is very thin. More will be the doping, less will be the depletion layer width, and that's why it will make a tunnel, right? And that's why the Zener mechanism is based on what? Tunneling phenomena. Remember that point, tunneling phenomena. Then application in voltage regulation, switching applications, and clipper circuit. So in operational amplifier, just to limit the signal, we are connecting the Zener diode back to back like this. This is one Zener diode. We are connecting the another Zener diode. This is called clamping diodes. But actually we want to limit the output voltage. We want to limit the output voltage like this. We can use as a what? Voltage limiter or what? Clipper as a voltage Zener diode. Then this is the photodiode. It is operated in reverse bias. Doping concentration slightly less than the normal PN junction. Photodiode means what? When we are giving the light in the junction, in a depletion layer, new hole electron pair generated, and the current will increase. But actually it is a reverse saturation current. It works in reverse direction. Breakdown voltage also works in reverse direction. It also works in reverse direction. And we are giving the radiation in depletion region, and because of that, new hole electron pair is generated, and Thus negative will attract hole is moving towards p side, electron is moving towards n side, and it will constitute a current, and that is called reverse saturation current, and it will increase because of that radiation, and that is called what? Photodiode. Remember, that is called what? Photodiode. It is a special diode, and it is used as a what? Detector. It is operated in reverse bias, doping concentration slightly less than the normal PN junction diode. So here we are using the less doping concentration, right? Then photodiode IV characteristics. This type of IV characteristics we are getting because it works in reverse direction. That is the reverse saturation current. We are giving the radiation, reverse saturation current will increase from this point to this point to this. Radiation intensity increases, reverse saturation current will increase. That is in third quadrant. This is first, that is second, this is third, and that is the fourth. So both voltage is negative, current is also negative in case of photodiode. So that is the photodiode. Now that is, we are giving the radiation, and that is the characteristics. Now photodiode responsivity, this formula, remember, R is given by IP upon P incident. What is the photo current and what is the radiation? That is what? Incident optical power, and what is the photo current. This is a very, very important formula. Please revise that. You can get direct straightforward question on that. 2 marks question on this, guys. This is the responsivity. IP upon P incident. That, what is the responsivity? Photo current upon P incident optical power. That will give you in the question. The responsivity of silicon photodiode is a measure of sensitivity of light, right? It is defined as ratio of the photo current to incident light power at given wavelength. In other words, it is a measure of effectiveness of conversion of light power into electrical current, guys. Then solar cell, guys. Solar cell, again, we are not connecting any battery here. We are not connecting any external battery. In photodiode, we are connecting extra battery to make it what? Reverse bias. But here we are not connecting extra battery. This is the internal structure of solar cell: front contact to external circuit, anti-reflection coating, N-type silicon, P-type silicon, back. But they will not give you the diagram and so on. So what is the working of the solar cell? Here it works in what? Which quadrant? That is in what? Fourth quadrant, guys. And there will be the 2 important formula. One is called short circuit current and open circuit voltage, guys. So I'm going to give you the idea about that. What is the short circuit current and open circuit voltage? Now watch this. In case of solar cell, this is the solar cell PN. Here we are connecting a resistor, only resistor, no external battery. Here we are giving the radiation. When we are giving the radiation, because of that, voltage will develop and there will be a one current, and that is called photocurrent. Photocurrent will move in this direction and it will generate a voltage across the resistor. And because of that, this is the photocurrent IL or light current. And now it will become forward bias V. We will make this junction forward bias, and because of that there is a forward direction current. Forward direction current is given by reverse saturation current e raised to power V upon Vt minus 1. V minus Vt up minus 1, that is the IF. Now forward current. Now what is the resultant current? Resultant current will be always in this direction, I. Resultant current is given by light current or photon, that is the current because of light, minus what? IF. Minus of what? IF. Now, so this formula will become light current minus I naught e raised to power V by Vt minus 1. Okay, and I naught is the reverse saturation current. Now from this you will get the 2 formula. One is called short circuit current. Short circuit current means when we are making R0. So R0, then it is not short circuited, therefore V will become 0. So this is called ISC. ISC is nothing but light current, short circuit current. Because that V will become 0, 1 minus 1, it will become 0. So ISC is the short circuit. And now second, when R is infinite, you will get the V open circuit. And in that case, the current will become 0. You can make this current 0. So it will become IL minus I naught e raised to power VOC, open circuit voltage, upon VT minus 1. Now from that you can find what is the open circuit voltage. Here it will become IL, this is I naught e raised to power VOC by VT minus 1 is equal to IL. So IL upon I naught plus 1, and then you can find the what is the open circuit voltage. VT log of 1 plus IL upon what? I naught. VT log of 1 plus IL upon what is the IL? Light current. What is the I naught? I naught is the reverse saturation current. Or when it is divided by A, JL upon J naught, that is called current density. So this is called open circuit voltage. So you have to find the two things. One is what? Open circuit voltage. One is called short circuit current in case of solar cell. Now they will give you what? One extra characteristics for that. What is the extra characteristics? Simply, this is the quadrant. It is in fourth quadrant. Always remember that will be in the fourth quadrant. Why it is in the, no doubt I am making this, but actually this characteristics is in fourth quadrant. Why? Because current is negative but voltage is positive. Current is negative but voltage across the diode is positive, like this. And current is moving in this direction. And that's why this voltage is positive. This is called what? When the current is 0, this is called open circuit voltage, and this is called what? Short circuit current. Now, so just it is a open circuit voltage. This is called short circuit current. And when we are making a by trial and error method, we are getting the maximum product here, VM/IM. This is called maximum output power. This is the VM, maximum voltage. This is the IM, current. This is the product is maximum here by this is the characteristics, and we are getting the maximum product. And here one factor it is given, field factor. What is the field factor? VM/IM upon VOC into ISC. So they will give you what is the field factor, what is the VOC, what is the ISC. You have to find the VM/IM, that is called maximum power output. And the power input is given, then you can find what? Efficiency. You can find the efficiency of the system, guys. So that is a very important question on solar cell. Okay. So that is the case. So this is a very, very important one. Then in efficiency, you have to find the output maximum power upon what? Incident power, that is the how much power is converted into the output power, that is called what? Efficiency. Remember that characteristics will be in what? Fourth quadrant, because voltage is positive, current is negative. It is a fourth, and no need to apply any external voltage in case of solar cell. So that is about the solar cell, all the important formula. Then guys, after that, what is the application? Satellites, solar farms, remote lighting system, automobiles, and so on. Photodiode application, barcode scanner, position sensor used in the safety equipment such as fire and smoke detector, optical communication as a detector. So these are the application of photodiodes, photographic flash control. So this type of question in what? MSQ. In MSQ they can ask LED light emitting diodes, guys. Also already I have given, we are using the direct band gap semiconductor for light emitting diodes, that is LED, like what? Gallium arsenide. And when the junction is forward bias, remember LED is working when the junction is forward bias, in forward direction. Photodiode works in what? Reverse direction. Okay. Solar cell, it is in fourth quadrant, no need to apply any battery, but current will be in negative direction, N to P side, but LED, it is a forward bias. Zener diode works in reverse direction. When LED is made of direct band gap material, LED is monochromatic incoherent light sources, works on the principle of stimulated absorption and spontaneous emission. So this is about the LED, guys. Okay. Now these are the material. Silicon, what is the band gap? 1.1, germanium 0.6, gallium arsenide 1.4, gallium arsenide phosphide, that is 2.3, and gallium nitride, that is the 3.4. So sometimes they may ask question, but in GATE exam, normally they are asking what? Numerical type question, but MSQ they can ask, because in a special type of diode we are getting the theoretical question. So this, please note that important parameters. What are the applications? Smartphone, TV backlighting, traffic and rail signaling, LED display. अब तो सब जगह LED का यूज हो रहा है भाई. The laser stands for what? Light amplification by stimulated emission of radiation. Laser works on the central concept of converting electrical energy into high energy density beam of light through stimulation and amplification. Right, so that is what laser, but normally we are not getting question from this topic. So okay, just get the idea about the full form, and that is what special case of LED. What are the application? Optical communication and storage, laser matching and cutting, military and defense, laser imaging and holography. Hope. So this is about the special diodes. Already I have covered some special diodes and BJT and so on, guys. So I think I have given idea about all the topics, but you have to revise all the formula notes. You have to solve the previous year question. Right, okay. Then चलिए आज का सेशन तो हो गया. This is first of all install the BYJU'S exam prep app from Google Play Store at 9 p.m. Again I am having one class where we will solve 5 questions on Clipper on app. So you can install the BYJU'S exam prep, and this is the leaderboard, number of participants, what is your rank, each and everything is mentioned here, what is your score. And then guys, we are having the courses. That is what one crash course is going on, and one course what Vision Gate 2025 and 2026. Live classes, recorded lecture, study material, practice quizzes, mock test. You can enroll. For more detail, you can call at this number. Okay, at this number. Then this is my channel Electronics by Sanjay Rathi. You can join. I will upload the PDF of this session on that Telegram channel, and because of some problem I have to recover that PDF. If it is possible, then I will upload. Otherwise, you can revise this session through this video. And then finally, just from 9 p.m. 5 questions on Clipper. If you are interested, then join me on BYJU'S exam prep app. Okay, so thank you for attending the session. You are on BYJU'S exam prep. Subscribe the channel, like the session, and share the link of this session. And that is the EDC in one shot. Stay tuned with us because बहुत सारे सेशन और होने वाले. Thank you and good night.